All right, well, we will get this kicked off. Good morning, afternoon, or evening, depending on where you are coming from. I know we've got a nice global audience, which is great. So welcome to the 2024 Global GPR Congress. Just a quick moment to thank all of our sponsors currently listed on the screen there. Without their support, we couldn't offer this for free, which is really great. So we're happy to be able to do that. And we'd like to kick it off right away with Radar Love presentation by Stephen Twist, Project Manager for Atlas Geophysical Limited. So Stephen, I will turn it over to you to get us started.
Thank you very much. So let me just share my screen and we'll dive right in.
Roads? Where we're going, we don't need roads.
Well, regardless of what Doc Brown just told Marty there, we do still need roads. In fact, here in the UK, we have nearly 250,000 miles of road. So come with me as I take you on a journey down memory lane and highlight some of the early applications of GPR for pavement investigation here in the UK. I'll show you what it was like to conduct a GPR survey at the turn of the century and how innovative work by my colleagues and I foreshadowed what was to come in the future of GPR systems. There'll be pictures, data examples, and maybe the odd meme to help illustrate that GPR is a great tool for pavement investigation, but probably not at 88 miles an hour. I'm Stephen Twist, and I've been using GPR as well as other geophysical techniques to locate buried stuff for about 20 years. And when pushed for a little more explanation, I often say that I provide construction and condition information for the built environment. Now, I hope that at a GPR conference like this, I don't need to explain that GPR is an acronym that stands for Ground Penetrating Radar or Ground Probing Radar, or that the ground part is actually a misnomer. This technique can be applied to almost any structure, and there are entire sectors of our industry that rarely, if ever, penetrate the ground with their radar systems. A while ago, I did a LinkedIn series called #RadarLove, where I took every letter of the alphabet and described where I'd used GPR over the course of my career. I've investigated airport runways, brick walls, catacombs, castles, concrete beams, concrete slabs, railway track beds, roads or pavements, and those words are pretty much interchangeable, tunnels for both animals and humans, and of course, utility mapping. But as far as I can recall, this was my first job. First job was to locate the steel dowel bars at the joints within a concrete road, and these bars are at the traverse joints across the road. They allow for the partial load transfer of the wheel as it moves from one slab to the next. And what the client wanted to know was the exact position of the bars on either side of the joint, as well as any potential voiding below the joint. What that meant was not only was the cover detail, so the thickness of concrete above the bar required, but also the position of each bar and any potential lateral deviations across the joint, coupled with enough GPR data to provide information relating to possible voiding. Now remember, this was a long time ago, and this was the setup. Now, as you can see, we gave, just at the bottom, we gave each joint a unique number. Now, I can't remember how many there were in total, but each concrete bay was about 3 meters long, and the TM, the traffic management, went on for miles. Now, this was long before array GPR were on the market, so we had to come up with our own, and this is what it looked like. Now, again, apologies if this photo isn't the greatest, but this was back when digital cameras were high-end bits of kit, so it's likely that this photo is actually taken on film. What we came up with, as you can see, is 3 1500 megahertz GSSI antenna connected to a SIR-10. Now, the SIR-10 was our workhorse. It's a 4-channel system, and I'm told that the H stood for highways. And what that meant was we were able to collect more than one GPR profile at a time. But the SIR-10 would often jiggle its radar board loose from its connection, so I became pretty adept at taking that thing apart in a lay-by on some road somewhere. So anyway, back to the first job. As you can see, we're now able to collect 3 profiles at the same time. 1 profile on either side of the joint and 1 profile along the joint, all triggered by that small odometer wheel you can see out the back. The analysis involved processing all the files in the same way to ensure that there was parity across the whole dataset. Therefore, any one joint could be assessed against any other joint along the road. Now, this is the best bit. This is where I had to identify the position of each bar in each profile. So remember, 3 profiles per joint, 10 bars per joint, and a joint every 3 meters. That's around 30 picks per joint and well over a kilometre of road to survey. So I don't think I'd be far off if I said there are over 10,000 picks in the data. For the GPR processing, we used ReflexW, and I spent a few days picking the hyperbola in each profile to assign each one an XYZ coordinate. I then created a spreadsheet in Excel to import all of those XY positions and assess the depth and deviation in both a statistical and graphical way. Now, I know what you're thinking, okay? And sadly, this was a long time ago in a galaxy far, far away, but I do have data examples later on, I promise. So that's where it all began for me. It was pretty obvious that pavement inspections were going to be big business for a fledgling Mr. Twist. And our sales team did a great job in providing work with us so that we could carry out GPR surveys for pavement investigation and provide information that even the latest digital twins still don't have. And I've been doing this for decades. And the pavement management system is a great example of that. This is a high-level database that stores all sorts of information about the road network, from the signage above ground to the construction and condition information below the ground. To feed data into that PMS, we would use our multi-frequency array GPR system. And remember, this was back when Barry Bonds was hitting homers. I hope I got that bit right. Anyway, this was my home from home. As you can see, the GPR here is set up in the back of a Land Rover Discovery. And it's got a seat there for the operator, which was me, and 2 desks. That's right, we needed 2 desks. Under the right-hand desk there, the blue box you can see is the CER 10. And on top, there's a monitor for the CER 10. The monitor we used was a PC monitor, as it was much more streamlined. And we also needed a keyboard, which you can see on the extreme right there, because there was no touch screens back then. There's even a little thermal printer in the middle of that desk, which would allow me to print out data for QC purposes. On the opposite desk, you can see obviously the book for taking notes, but also the little cylinder, little white marker switch there, which will become important later. Now, the data acquisition was controlled by this odometer wheel, which was a repurposed moped tyre. And this would allow us to alter the trace increment, so the space in between each scan, so that we could survey at different speeds, because this was back when GNSS was still in its early phase of adoption. So we would use the little manual marker switch that I showed you earlier to put marks in the data and tie that back to known locations on the road network. Now, I'm going to show you a screenshot from Google Street View. And if you live here in the UK, or if you come traveling over here, it's going to change every motorway journey you ever have. These 2 little white dots are called nodes, and they mark sections on the road network. And now that I've pointed out their existence to you, you will see them everywhere, because I know I still do. The asset owners break up their entire road network into much smaller sections, and these nodes mark the start and end of those sections. They're commonly found at significant points along the road, so before and after off-ramps, or at significant structures such as overbridges and underbridges. But the significance to the GPR user is that we're able to place manual marks in our data and highlight the start and end of those sections. The driver would shout, "Mark approaching, mark," and that would alert me, the operator in the back, to pay attention and prepare to click that marker switch to place that mark in my raw data. We would also use marker posts. These little white marker posts sit at the side of our motorways and are positioned every 100 meters. And I deliberately use air quotes here because we would sometimes measure how far apart they exactly were. And let's just say there was some variance. Now, I know what you're probably thinking. With the speed we're traveling, my reaction time, the parallax, the variation between the marker posts, this would all reduce the accuracy of my mark. And you were correct, that did come into play. But I just happened to be really good at it. Now, as I said, the asset owners actually knew the distances between the start and end of those sections, and my fiducial marks were really just a cross-check to ensure that we were collecting the correct amount of data per section. We would always carry out an odometer calibration before data acquisition, and we would regularly maintain the wheel and carry out routine calibration checks. And what we found was that our GPR data lengths were always within a few percentage points of our clients' distances. And even with the variation between the marker posts, we could always omit a few from the distance calculation and find that over a larger distance, our measurements were always well within acceptable tolerances. Now, I talk of a multi-frequency array GPR, and using the SIR-10, we would usually attach 3 antennae, and they would hang underneath the vehicle in the near side wheel path. We would use a 1500 megahertz antenna for the surface dressing layers, which you can't quite see in this picture because it's at the back. We use a 900 megahertz antenna for what I refer to as the bound layers, and that's the black rectangular box at the back. And then the 400 megahertz antenna, which is the large red one, that would allow for a deeper depth of investigation into the sub-base layers of the pavement and sometimes beyond. So there you have it. There's your multi-frequency array GPR system. And this would allow us to provide our clients with pavement layer thickness data that would load straight into their PMS. And again, this setup allowed us to travel at traffic speed. So there you go. Multi-frequency array GPR, capable of traffic speed data acquisition, so no need for traffic management, that provided data into a database that allows for informed maintenance schedules and lifecycle performance analysis. All feels very modern. Now, it's at this point where we start to divide the pavement investigation into 2 types. Those who want pavement construction information and those who want pavement condition information. Sometimes these 2 requirements did combine, but by having 2 distinct objectives, we were able to create a different survey approach for both. For construction information, the client really wanted a simple representation of their road construction. So we came up with the summary construction reporting format that would simply identify the average material thickness for each layer between 2 construction changes. Now, of course, this led to discussions about what average was and how we define a construction change. But put simply, where we're able to detect material changes, we would introduce a construction change, and those material changes were sometimes confirmed by core information. We would also identify significant jumps in material thickness, and they would require a construction change. So in the GPR data, if the boundaries weren't continuous, we would introduce a construction change. We were also able to identify where there were numerous layers, and this would suggest patching or overlay construction. And again, those would be triggered a construction change. Then between each construction change, what we would do, we would identify each layer with a simple single pick, and that would create a block style chart that was easy to read and fast to create. In fact, it was so fast to create that it became cost effective enough for us to head out and speculatively collect GPR data from our client's road network. Our team would head out and drive around collecting data for 5 days a week, and then we would call our clients and say, we've collected your data, would you like us to create some charts for you? To collect the summary construction information, we'd set that trace increment to 2 scans a meter, and it allowed us to travel at traffic speed, but it still provided us with enough data to identify those material boundaries and those construction changes. However, for condition information, we needed a much denser scan rate, and often this would be determined by what the target was and whether the road contained steel reinforcement or not. I always considered these types of survey more of an investigation where the parameters of the survey design are set by the expected outcome. Anyway, let's fast forward a little bit now and move forward to when I worked on away from the commercial sector into a research project that I assisted on that was funded by the European Commission. As part of a collaboration, I worked with representatives from the Netherlands, Italy, Greece, and the UK to investigate how the integration of multiple technologies could improve the approach to pavement investigation. The notion was to combine advanced technologies, namely video, thermography, ultrasonics, and GPR, to collect traffic speed data to to determine if we could detect surface and subsurface defects at speed. We were able to acquire data while traveling at traffic speed by towing a custom-made trailer that would house the GPR in the middle there, in between those two white blocks, and then the ultrasonics, which is the cylinder on the back that you can see there. And the cameras are mounted on the roof of the vehicle as shown in the first image. Now, as the expert, of course, I knew it would be possible to detect subsurface pavement defects with GPR, particularly as we were using a GSSI system with a 1500 megahertz and a 900 megahertz. But what was great to see was how the experts from other fields were able to combine and bring together a truly integrated system that would add information to the database to improve interpretation confidence not only in the GPR data, but in all the techniques. I was particularly impressed with the software that was created, and I know what you're thinking. We will get there. Here we are. We have some data. What we're looking at here is along the top row is the thermography imagery, and we can see the white spots in the first image are the hot spots. The next two images are the thermography again, but in plan view, alongside the video feed, and then the GNSS located map, which would show automatically the position of those highlighted hotspots in the video and in the GNSS data. On the second row, we can see the low frequency radar and the high frequency radar, the blue line and the red line tracking those material boundaries as we go along. The black vertical lines are the interpretation of the IRT shown on the data as we collect it. And on the bottom row, we can see the color chart from the GPR data, which shows that material thickness from the blue boundary. And next to that is the ultrasonics data, which shows the increased level of response that's possibly related to material separation. So there you go. All very exciting stuff. And again, this was 8 years ago. Now, not all pavement investigation is about asset management. There's still work out there for particular situations when a particular need has arisen. So I want to share with you some real world data and not necessarily the textbook primo data that's usually shared at this sort of event. So this is everyday data that we collect here at Atlas. For us, this project was a combination of the three amigos, GPR, FWD, and Cori. The client asked us to survey a short section of pavement to determine the thickness of asphalt and the stiffness characteristics of the road. We deployed our FWD for the stiffness stuff and our GPR to provide the material thickness, because the FWD often requires material thicknesses for optimal back analysis. Both methods were collected down the centre line of a single carriageway road, which was a relatively new road at the time. So what you're looking at here is a radargram from a 400 megahertz antenna. And if the scales aren't very clear, that's about 100 meters of road, and it goes down to about 800 millimeters in the vertical. The vertical red bars that you can see are how Reflex displays core information. The process of inputting the core information into Reflex is to collect the core log from the driller and determine which of those pavement layers form your interpretation layers. Now, hopefully you can see that those magenta and blue responses in the GPR data show the different materials in the pavement. And again, I hope it's clear that you can see where the locations of the bottom of those bars, or the cores, correspond well with those magenta boundary, or that magenta boundary, at around 150, 160 millimeters. Now that's by design, because we're able to take the core data, the truth data, the physical representation of how thick the asphalt is, and adjust the velocity in Reflex so that it calculates the two-way travel time, and it allows Reflex to display the radargram, so as far as practically possible, as far as reasonably practicable, that matches the physical reality of the core. Now, of course, there are loads of reasons why the discrepancies could occur, but it's important that these are managed. One of the main reasons that I've encountered for the discrepancy between core data and GPR data is simply location. Actually locating the core, recording that location, sharing that location, and then recreating that location in GPR data can lead to a number of small location errors, that variance I talk about. Because you could see if any one of those cores is located in any one of the different position along that radargram, it may not necessarily match with that boundary. So to manage that variation, We like to collect the GPR data first and use that information to target the cause. That way, we can target areas of poor resolution so that it will assist with the interpretation, but also into control areas, places where there is a consistent strong boundary, and that will then give us confidence in the interpretation as a whole. It also allows us to direct the coring teams with either a GNSS location, if that technology is available to them, or with a real-world measurement from a known structure, such as a bridge or a manhole, because that's what's happened here. You can see in this data, those surface reflectors that echo or ring down through the data are actually manholes. We're able to give measurements back to the driller to say where we would like the core to be. Okay, so this is another example of a typical GPR investigation that we conduct here in the UK. What we're looking at again is a short section of GPR data which shows good correlation between the thicknesses as determined by the core information and the GPR data. In this example, it's possible to identify more than one layer in the GPR data. And once you've identified the material boundary in one location, it's possible to follow that boundary and identify the material type in other locations. The initial example was taken from a fully flexible road, but here, because we can identify that lower base layer, we can identify the concrete layer and classify this as a rigid construction. Okay, so what's the current state of play? Well, if we're looking at pavement investigations, there are lots of systems out there on the market from when I first started. It seems that pretty much every GPR manufacturer has a GPR array of some sort, and these are just a few examples that turn up with a simple Google search. So kudos to you and your SEO if you see your system here. These new systems often have a dedicated vehicle to allow for rapid deployment times, fast acquisition speeds, and cover much larger areas. The data is often geo-relocated using RTK GNSS, but also IMU to reduce the impact of dead zones from the GNSS. This all leads to statewide surveys with huge vehicles recording lots of data. But for me, despite the huge leap forwards in antenna manufacturing, processing power, ease of deployment, it's the inclusion of RTK GNSS that's made a huge difference. It not only removes the need for those manual markers, it's also allowed for data to be curved and manipulated so that it can be loaded into a map instead of into a simple engineering drawing. So this is an example from an airport taxiway that we surveyed. What we've created here is a time slice to show the amplitude variations that possibly relate to voids. To create the time slice, we take a window of time that relates to a specific depth below the ground and sum the amplitudes in that region. Where those amplitudes are high, we get red and yellows. And it's these areas that we then investigate in the radargram data to see if we can correlate a response with them there. Often, these types of responses are from metallic objects at the surface, like those manhole covers we saw earlier. And those high amplitudes ring down like an echo, and they manifest at depth where they don't actually exist. So the interpretation then becomes a case of removing that ringing effect or another noise. Usually we cover those over with a hatch pattern in an interpretation drawing, and we highlight the other areas that were potential voids. And for me, this has really created buy-in for the client. It's made the data easier to understand, and you can visually see where the defects are. And sometimes it helps understand the failure mechanisms that the clients may have a better understanding of when they can see the data on a map. So there you have it. GPR investigations remain one of the key parts of my career, even though Future Day has passed and I still don't have my hoverboard. So in closing, can I just offer a few thank yous? First, I'd like to thank Dan for reaching out for me and giving me the opportunity to speak today. Of course, the organisers for putting on the event and the sponsors, and to Alex Birtwistle from Atlas Geophysical for getting to geophysics in the first place, because he was the guy in the very first photo, and subsequently being gracious enough as a boss to give me time to put the presentation together. And finally, a thank you to all you attendees, and I hope that you found this either enlightening, interesting, or at the very least, entertaining. Thank you.
Awesome, Stephen. Thank you so much. I really appreciate you participating and giving us that. I mean, both history lesson and um, great information for folks. I mean, I think something that I've seen, obviously, in the recent past in geophysics and GPR, are people expanding the applications that they're utilizing GPR for, within a given uh, company, right, or corporate entity. And where a lot of times you had folks that were doing sort of utility locates or concrete scanning or investigations or archaeology, and that was the focus. There's really, I think, been this recognition that with the development of hardware and software, people can start to get at, right, some of these other applications. And I think that what you provided hopefully helps a lot of folks sort of to start to breach that roadway and pavement analysis piece. So I'm going to turn it over to everybody over, that's attending and who watched it. Put your comments or questions in the chat, and then this way Steve can sort of go ahead and answer them. So here, number one, first question from Christopher Bryant. How did you avoid interference between the three antennas? I guess he's talking about that original SIR 10 that you had showed, with the three different antennas, coming up on that joint. Where did you capture interference there between the antennas? Were they, triggered at different timings, or sort of what did you find, I guess?
The short answer is yes. There was lots of interference back then. But don't forget, we were looking for very broad scale patterns and trends in the data. So high frequency noise, scatter, all those kind of things. They didn't really impact the noise to signal ratio that we were looking for. We could still identify our material boundaries. But yeah, that did happen. There were often places where you would extend boundaries through noise based on the fact that for the last kilometer it's been 100 mil of concrete, so for the next 20 meters it's going to be the same. But yes, that was definitely a problem back then, and obviously antennas are much better now, much better shielded. We don't experience the same interference with the digital antennas we have now than we did with those analog ones back then.
What was the, and you probably said it and I might not have caught it, what was the frequency of those? Because obviously you showed some of that 400 data, but for those small antennas that you packaged together, what was that frequency?
So typically we would use three frequencies, as you said, the 400 data from the red antenna that I showed, and then we used a 900 megahertz antenna and a 1500 megahertz antenna, and that allowed us to do the surface dressing layers from the high frequency, the bound layers, which is pretty much all of the pavement construction from the 900, and then the 400 would get down into the sub-base layers and potentially deeper should we need to do anything in the subgrade.
Quick question, just to sort of layer on top of that. Back then, 1500 was considered a pretty high frequency. Obviously now, there's been development to 2.7 and 3.5 and continuous wave and all that. Have you seen higher frequencies impact the the deployment of GPR for roadways, and sort of has that been helpful in finding greater variability in the subsurface, especially at ultra shallow depths?
Yeah, I mean, we were one of the first to use the gigahertz range antennas again back then, 20 years ago, and we hung those way out the back of the vehicle because obviously we didn't want any interference. They were air launched antenna, and what we found was as we were a global survey company, we would go to countries where they were using chip seal road, very thin layer, so we wouldn't take any of the higher frequency antenna from here. We'd just take the giga horn, the 2.6 horn antennas, and use those. But yeah, the higher antenna frequencies allow us to get that thinner construction that we don't necessarily see here in the UK, but globally we had seen and investigated. Yeah.
So from like a an asphalt versus base, right, layer, obviously asphalt sometimes is ultra thin and it's tough to sort of resolve. Have you found that newer antennas, especially with those pushing those higher gigahertz frequencies, has been helpful in resolving you know, 1 inch to, or, you know, a couple centimeters,
Oh,
you know, of asphalt.
absolutely, and it also helped to then explore different failure mechanisms and raveling and all this kind of thing. You know, things that we weren't necessarily able to distinguish because of the surface dressing layers and the subsequent layers. As the frequencies have got higher, we can then start to say it's actually the surface dressing layer that's peeling away from the below layers and things like that. So, yeah, it gave us more analysis that we could then present to the clients to give an idea of what potential failure mechanisms are going on in the pavement.
Sure. All right, here's another question from the comments. It says, this is from Abdul Hakim. Thank you for the presentation. Could you please explain how GPR is used for cavity detection under, well, existing buildings? You know, I guess kind of pushing that over to maybe the example you showed, which was on a runway or tarmac, you know, as others might call it. You know, what sort of, what do you dive into there? And obviously in the next presentation, we're going to get a whole lecture on polarity shifts, or whether or not they happen. So kind of from your perspective though, what's your, what would be your workflow, right? Because obviously finding cavities versus finding other objects or defects underground will be different. How does sort of that, you know, play out for you guys at Atlas?
So it all comes down to that contrast. Is there a contrast? You know, why do you think there's a cavity there? What's in the cavity? Is it water filled, air filled? You know, here we have bomb shelters that are under buildings often, and that'll have a small gap because they tended to have backfilled them by now. So you're looking for a small air gap, but again, sometimes you're looking for a water filled cavity. So it really depends on what that contrast is. And I always say that you know your survey design really informs the methodology. So if you go to a client and say, yeah, we can come to your building and have a look under the floor and see if there's a cavity there, but actually there's 2 layers of reinforcement and we can't necessarily see through that, then maybe GPR isn't the right technique for that. And there are other, obviously, geophysical methods that we can use. And space is the other one, the actual physical space you have. If you're looking for a cavity that's a big cavity, but it's inside a building, if you're looking for karstic scenery in the geology, for example, then obviously you're going to be restricted to what size antenna, how low your frequencies are going to be. So these are all questions and conversations we have at the client inquiry stage that allow us to make an informed survey methodology decision. And yeah, GPR for cavity detection is great. My dissertation was looking at catacombs, and I surveyed across the top of the catacombs looking for the void inside the catacomb. So yeah, it can be really great application inside a building looking for voids under buildings. Yeah.
Yeah, I think it's a really good point that you make as far as like how much space do you have to work. You know, we had been asked one time to investigate and find, you know, whether or not there's cavities underneath a roadway in sort of a pretty densely, you know, populated urban environment, and the entire area, right? There were no anomalous signatures because underneath the road was a parking deck, right? So the whole thing was a cavity, right? But there wasn't like a contrast, so you really had to dive in, right, to sort of this deeper analysis and okay, you know, what should we be seeing from the waveform that's coming back? Where usually, like in the image you showed, hey, if we can pinpoint some anomalous, you know, responses and then dig in, is it water, is it air, is it just metal, you know, or whatever. But if you don't have the perspective, right, in space, it's hard sometimes to sort of do that analysis. All right,
Yeah.
a couple more from the comment section. From Forrest Sim, from the perspective of GPR pavement analysis, what are the most interesting and exciting advancements in ground penetrating radar? Are they hardware advancements, software? You know, what in particular? Yeah, what do you see coming?
Yeah, I see. Coming in the future.
Yeah.
Okay, coming in the future. I think it will be that decreasing the trace increment. I think getting more detail, but still traveling at faster speeds. You know, allowing us to then not only collect the pavement construction and condition information, but then obviously big business here in the UK, utility detection. You know, the amount of times we go out and do a road survey for asphalt thickness, and they ask us to find the utilities as well. And you know, you have to have the conversation that we're not collecting enough data to identify the utilities. So I'd love to see rapid data collection for tiny targets. And again, I assume, not knowing much about this kind of stuff, that's a processing power speed thing and dwell times and all of that stuff. And as computers and chips get quicker and faster, then we'll collect more and more data at shorter and shorter trace increments, and we'll just be able to see more in the data that we collect.
Yeah. What about, integrating different sensors, right? Obviously, you showed the infrared and the GPR, and sort of, helping inform one with the other is pretty critical. Do you see, over in the UK, folks using not just in-road work, but across sort of the board, folks using enough diversity and sort of sensor technology to make really informed decisions, or are you seeing that there's limits? And have you seen sort of those limits come from the users or from sort of the end client, where budgets are constrained and they don't want to sort of pay? I mean, what have you guys seen over there?
Yeah, I think sensor fusion, collecting multiple data sets, I always want to do that. Again, my dissertation, I fused my radar data with point cloud data. So I got 3D point cloud data and then tried to create 3D GPR data and put those two things together. Again, that was, 12 years ago, something like that. And again, with the project, I did the European funded project where we combined the thermography and the video. Again, that's something that happens here. The ARAN vehicle I showed there, that's got loads of sensors on it, lots of cameras, lots of surface defect stuff as well. So they used to, I'm not sure if they still do, you would send a man out literally to look at the surface and map where those things were. And obviously a man boots on the ground, that's person in danger, whereas if you can collect that from a moving vehicle traveling at traffic speed, it's much safer. So again, fusion of cameras and point clouds, all of that stuff I think will be great for the industry. Yeah, it's but again, they tend to be the high-end surveys. When you're collecting a large area network, you can have that upfront cost to buy all those sensors, fuse them all together. I think down the line where we operate, there's usually a requirement, a need, a fault. There's always something that's happened that's triggered the requirement for geophysics. And then that's the conversation you have as to which technique is applicable. And as I say, I often want to try and involve as many techniques as possible so that we can get as much back from the survey acquisitions we can.
Sure. Do you find that that's going to be easier for folks? Obviously, people joining today are from around the world, with different levels of expertise. You've been doing this for a long time. Obviously, you had formal training. Do you find that sometimes it's a little bit more inaccessible for folks, maybe early career, or who may not have exactly the formal background that you have? Do you find that sort of sensor integration, the ability to be able to manage those data and interpret them, is going to get easier with AI coming, or with software developments, and things like that? Or where do you sort of see that kind of playing out?
Yeah, I mean, even as far as just the GPR, the CER 10 required you to have a good understanding of the physics of what was going on with the radar signal and what filters needed to be applied, what gain needed to be applied. Whereas now, obviously, modern GPR digital antenna, they're wireless, even if they're not wireless, the control unit knows which antenna you've plugged into it. It knows what filters it should be using. It can automatically assess the gain. So you can pretty much guarantee you're always going to collect some great data. One of the things that used to happen back in the day with the 1500, so the higher frequency stuff, it would warm up and you'd lose the start pulse. So you'd actually lose the T0 correction. And it happened on a couple of occasions where we'd run a survey with a junior or somebody new, and they hadn't kept an eye on the start pulse and it had drifted off, and then you didn't know where the depth correction was coming from, so you had to go and repeat that data. So again, that's something that's been ironed out now. That doesn't happen anymore. And so yeah, things like that, advancements like that are coming along brilliant. Love to see that, as well as, like you say, the AI stuff, the automatic detection of things, mapping the hyperbola in that first example I gave. You could still automatically do that back then, but again, the QC process was so high that while you were checking the profile, you might as well just do it yourself. Yeah. Whereas now that's so much better, and you can train those thresholds much finer, that really it becomes a cursory look. Yes, it's picked all of the ones I would pick. So again, and that then allows me as the operator to then look on the tricky ones. So if it catches 90% of them, I can focus on the difficult 10%. and often they're the plastic water pipes or the deep gas pipes and things like that. The tricky ones, the ones that are obscure, not at 90 to your survey profiles, all those things that you need to give a bit more time to, you can, because the AI has identified 90% of what you want to find anyway.
Sure.
And what I would love to see come in is integrating that with the cable location stuff, the Cat and Jenny, the EML stuff.
Yep.
So actually being able to load that data onto my reflex data or onto my GPR data, so I can see where I've picked up with my EML, my Cat, and then say, okay, well, I should see a hyperbola here. I do, and that's the same gas pipe, that's the same water main, that's the same electricity cable.
Sure.
And again, that helps here with things like PAS 128, where we're looking for that double verification, that increased confidence in interpretation. So I think that kind of sensor fusion, that kind of combined approach to interpretation really helps and will really move us forward.
Yeah, it's great. And I'm definitely guilty, by the way, much early in my career, to letting my ground surface drift on my wave. And I did not want to go back to site, but you got to do what you got to do when you're young and you're still learning. Okay, so last couple questions really quick. One says, can you say anything about certainty about the shape and size of subsurface utilities based on GPR data? Sort of quick, response there, as far as sizing of utilities. I know it's, again, kind of outside the talk a little bit, but
I always shied away from size. I always thought that was a tricky thing to do, sizing with hyperbola, because of the velocities. And again, we never really show the velocity calculations here. It's usually a bulk velocity that's applied, especially when you're going through a layered system. It can be done, obviously. It's great if you're doing concrete, things like that, where you've got a more homogeneous material. For utilities, I've tended to shy away from sizing things. You can say it's bigger or smaller, but you can't
Sure.
necessarily, it's 6 inches or 8 inches. I tend to shy away from that sort of thing. But again, usually we can identify that with, we're expecting the gas main here. The gas main is 24 inches. We found it, so I know that that's the 24-inch gas main. So again, it comes back to drawing on all of that information, not just what your radargram is showing you.
Yeah, it's a great point. From Adam Cook, it says, are there any surveys you did in the past that you would love to have another go at with the latest technology? What sort of one that comes to mind? It's a great question.
There's Adam's very lucky he didn't appear in any of those photos, because Adam and I used to work together in those early days. If I knew he was going to attend, I maybe would have put him in. Any surveys I'd love to do back in the past? Oh, there must be loads. Yeah, a lot of the archaeology stuff, because I came to archaeology later in my career. So I'd love to go back and look at some of those earlier archaeology jobs, and especially with the array GPR antenna that we have now. The stuff that's being produced, especially here in Europe, the guys are just creating some awesome data. So yeah, maybe I'd love to go back now with a bit more hindsight, with a bit more archaeological knowledge, and identify some of those things.
Yeah, that's a great answer. All right, final question. Abhishek Kumar says, how important is the data density while acquiring the GPR data for subsurface utility detection, and what should be the optimum gap between parallel GPR profiles for creating accurate? It's pretty detailed. Aggregate 2.5D model. I'm going to sort of adjust it a little bit. Is from a data density standpoint, back to into the road surveys, because this is something that I've had discussions with folks about, where look, when you're thinking archaeology, you might have really small targets of interest and high density data collection, whether that's 4 centimeters apart or 50 centimeters apart, depending on what you're looking for. But when you go to road surveys, if you're looking for a defect of some sort that might be bounded, or if you're looking at layer analysis and what's the thickness, right? How does sort of application or almost like scope of work play into what your data density is? Does it have to be sort of right next to each other, or is 1 or 2 down the road, enough when you're looking at layer thicknesses? What's sort of been your experience?
Okay, so in my experience, it comes down to cost.
Sure.
How slow can I survey? How much money do you want to spend? Because I can put my scan rates down really fine, and we can find lots and lots of things for you, but it's going to take me a while to collect the data, and it's going to take me a while to process it, and it's going to take me a while to do the interpretation. So if you want to look for everything, we can do that, but then obviously the cost is increased. So it becomes then a balancing act. And again, that's where I like to have those discussions with the client. What is it you're looking for? How small is the target you're looking for? How deep is it likely to be? And then, how long have I got? Because
Sure.
that's the important part, I think. Yeah, clients sometimes are just ticking a box and they don't have the budget to spend on me to sit here for days and produce very fine detailed interpretations. They really are just wanting to know where the thing is and if it's there or not.
Sure. Well, again, thank you so much, Stephen. I really appreciate it. I'm so happy you were able to get the kids to school and get here for the for the presentation. We're picking them up from school, I guess, in your
Yeah.
time. Yeah.
The clock here is ticking.
Oh man. Well, again, thank you. I appreciate it. It was really, really informative. It was just it was fantastic to have you on, and hopefully we can continue to have this conversation into the future. And I'd love to talk to you some more personally. It's just a rich resource. And I follow not every letter, but I definitely was interested in seeing the applications of GPRs. You were doing them on LinkedIn. Yeah. It was look, it was like a fun thing to see when I'd pop on, a couple times a week or whatever. But thank you again. Really appreciate it. Everybody, you got like 2 minutes to take a quick break, grab an espresso or go to the restroom or whatever, and then we're going to have Davide come next with his talk. Thank you so much, Stephen.
Thank you, Dan.
Yeah. All right. Infrastructure resources team, can you guys queue up Davide?
Hey. Hi, Dan. I'm here.
Hey, Davide, how you doing?
I'm good, thanks. You?
Does he have access to share his screen?
I'm sharing. Can you see my screen?
Yeah.
Yeah. Okay.
But I just want to say, sort of before you start, Davide
Yep.
is the first return talk. He gave one last year. I don't know if it's the same or it's very similar, but it's backed by popular demand. And so in a survey afterwards, everybody was asked, who they'd like to see again. And well, all the talks last year were fantastic. Davide got the most votes. And so we really appreciate you coming back to educate us all again. I'm really looking forward, to it. There was so much information packed into your talk last year that I'm excited to sort of see some of this stuff again, or some of the new experiments that you've been running. So thank you so much for joining us, for a second year.
Well, thank you for the introduction. I'm pleased to know that my presentation was well accepted. So,
yeah, it was well received.
yeah, thank you very much. So, yeah, my name is Davide. I define myself as a GPR specialist because I dedicated basically my entire career to it. I'm hoping to dedicate more years to GPR. Currently, I work as technical manager at Amberg, a company in UK that provides GPR service, a GPR service basically for structural engineering. The presentation is about polarity inversions if we have them when we see voids. This is basically a summary of a few articles that I wrote years ago, a couple of years ago, and they are based on some sentences that we can find easily on the web, on articles, on PhD theses, or reports. Sentence like this one, voids cause polarity inversions. Like this one, voids start with a black wavelength band, and voids start with negative. And also we can find this formula for the reflection coefficient, which is the one that controls a polarity inversion, where epsilon R1 is the dielectric of the material above the interface, and epsilon R2 is the dielectric of the material below. But we can also find this formula, and obviously there is only one that is the correct one. So let's see what polarity is. If we have a look at an A scan, what we see is, first of all, the direct wave. This is called the GPR wavelet because of the shape. And we have, in this case, 4 peaks, 4 amplitude peaks. The first one is positive, then negative, positive, negative. In a real case, from a real GPR antenna, we can have 3 peaks or 2 peaks. It depends how the antenna is built, but that is irrelevant to us. When we have an interface, when the wave interacts with an interface, with the dielectric contrast, of course, we have a reflection. And we can have, instead of a positive peak at first, we can have a negative peak. All the peaks are inverted in terms of sign. That is an inversion. If we have another interface on another object, and the wave interacts with it, we have another reflection. In this case, we have again a positive peak at first. So we can define the polarity simply as the sign of the amplitude peaks, and we can use the first peak as a reference. When we speak about polarity, we need to remind ourselves that we have also the word polarization, but that is a different object. For polarization, we mean the direction of oscillation of a wave component. For GPR, we generally refer to the electric field, and the direction of the electric field is generally the direction of the antenna axis. If we use as a reference the scanning direction, this red arrow, so from left to right, we can define different polarization, different antenna configurations. That is the best definition. The one on the left, where the antenna axis is perpendicular to the scan direction, is the most common for most of the GPR antennas. If we rotate the antenna, we have this configuration which is parallel to the scan direction. You know that there are some manufacturers that produce antennas that can be rotated just by rotating the survey wheel, or they have both polarization, and you can collect the data at the same time with both polarizations. These two configurations are called perpendicular broadside or parallel broadside, depending on the direction of the antennas. But the manufacturers call them cross-polarized antenna. That is a wrong term, because a cross-polarized antenna is this one, where transmitter and receiver are crossing each other, are perpendicular each other. These two configurations are simply called copolarized. Coming back to polarity, when do we have a polarity inversion? When a wave interacts with an object, with an interface, part of the energy is reflected, a part of the energy is transmitted or refracted. It is the same thing. If we want to quantify how much energy is reflected, we need to use the reflection coefficient. We have two of them because it depends on the polarization. But for a common GPR application, the angle of incidence, and also the transmitted one, are generally very small because transmitter and receiver are close enough. So we can simplify these two formulas into this one. And this is the correct formula for the reflection coefficient. So it is 1 minus 2. We can do the same kind of thinking for the transmission. We have two formulas, one per polarization, but the simplified one is this one. So now, keeping in mind these two formulas, if we have a look at the sign of each coefficient for a different dielectric contrast, so when we move from a fast to slow material or from slow material to fast material, we see that regardless of the polarization, the transmission coefficient is always positive. And that means that by transmission, we will never have a polarity inversion. If we look at the reflection coefficient for perpendicular polarization, also the most common antenna configuration, we see that is negative when we move from a fast material to a slow material. And we know that air, a void, is always faster than everything else because the dielectric is 1. So we have a polarity inversion when we travel from a void to something and not the other way around, because the other way around is a positive coefficient, so no inversion. For the parallel polarization, it looks more complicated because we have an additional angle. This is the Brewster angle at which the reflection coefficient is 0. But again, because for our applications, our angles are very small, again, we will always have a negative coefficient when we move from fast to slow, and a positive coefficient when we move from slow to fast. The other conditions are valid if we do a CMP survey, or maybe not even there. So now let's have a look at some models that I built to verify what we saw theoretically. Here we have a layer with a dielectric of 8. This is a layer of air that I needed to build the model, but we can ignore it. And below this layer with the dielectric of 8, we have a multi-dielectric layer, so essentially 6 boxes, with the dielectric increasing from left to right. From what we saw so far, for the first 3 boxes on the left-hand side, we are in the condition we move from slow material to fast material, so we shouldn't have a polarity inversion. We should have a polarity inversion for the other 3 boxes. If we check a wave propagating, this is our direct wave. It starts with negative. It interacts with the boxes, okay? This is the transmitted wave. It appears like a staircase because we have different velocities, of course, but they all start with negative. So we see that we didn't have a polarity inversion because it is a transmission. This is the reflected wave, the one on top. For the first 3 boxes, we see that the negative is the first band, so no inversion. On the other side, we see that we have a positive band, so we had the polarity inversion. We can see the same in a radiogram. We are more familiar with radiograms, obviously. So negative on this side, no inversion. Positive on this side, inversion. If we want to make the radiogram a bit more realistic, and we add these homogeneities, this is what we get. The interface is still there, but apart from the fact that it is not visible in the center part of the radiogram, here it looks that it starts with positive, so we have an apparent polarity inversion, but that is caused by the attenuation and by the scattering of the signal that extracted energy essentially from the wave. On the other side, maybe we have a tiny weak positive, but in a real case, that would be probably a guess job. So if instead of looking at the radiogram, we look at B scans, one on the left-hand side, one on the right-hand side, we see that, of course, the direct wave is the same for both of them. It starts with negative. The first peak is negative. On this side, for the red line, the red A scan, we don't have a polarity inversion. The first peak is negative. On the other side, we have a polarity inversion, and the first peak is positive. And we see that both of them are very close to zero in terms of amplitude. If we add our heterogeneity, the two direct waves are no longer the same because they are not in the same position and because the radiogram is not homogeneous anymore. Here it looks that it starts with positive from the radiogram, from the B scan. If we check the A scan, instead we have a weak negative, very close to zero, but it is still there, so we have the inversion as it should be. On the other side, here we can't see anything. In the A scan, instead, it looks that it is negative as well. Actually, it's positive. It is a bit delayed because all the heterogeneities have a different dielectric, and the interface does no longer appear always at the same time. So we have the situation as it should be, but it is very complicated to assess, even with an A scan. So now let's have a look at the air-filled voids, still simulations, not real data. We start with the circle. That could be an empty pipe, plastic pipe, obviously. So we see our wave propagating towards the top of the circle, the top of the pipe. It starts with negative, and this is the direct wave. Part of the energy is reflected, still negative, the first band. Part is transmitted, negative, no inversion. Here we have a multiple generated by the top surface. This is a common situation. The transmitted wave almost reached the underside of the pipe, but we have also two creeping waves. A creeping wave is a wave that is diffracted along a smooth surface, which is a circle, a sphere, or a cylinder. What we have here is that the transmitted wave was reflected back. It starts with positive, but then the two creeping waves interact with it, and what we have as a result is a wave propagating upwards that we think is our reflected wave, but it starts with negative. So there is no polarity inversion, although we expected to have one. If we see a radiogram, the corresponding radiogram, direct wave starts with negative. Top of the pipe starts with negative. Bottom of the pipe starts with negative as well. Here we have the multiples, but they are not relevant to us. If we make it more realistic, direct wave starts with negative. Apparently, the top of the pipe starts with a positive. So we have another apparent polarity inversion. If we check now a square, that could be a hidden room, scanned from above or scanned from the side, from a wall. Again, our direct wave, partially reflected, partially transmitted, no inversion in any case. Here we have two side reflections. How do I know that they are side reflections and not creeping waves? First of all, because creeping waves for a square, I don't think they are possible. But in any case, if we check the polarity, they start with a positive. So their polarity has been inverted, which means there has been a reflection from the side. The transmitted wave is reflected from the underside of the square, so it starts with positive. And these two waves, they interact with the underside as well, with the corners, and we will have these two waves. they are reflected, so they are inverted again, and they will start with negative as per the direct wave. And this is what we see in the radiogram. So direct wave is negative, top of the surface is negative, multiple, bottom surface positive, the two hyperbola branches from the side, from the corners, they start with negative as per the direct wave. In a more realistic radiogram, again, the top of the surface looks that it starts with positive. Now we have an arched structure. When do we have it? When we scan for a vault, above a vault, when we scan a bridge, a tunnel. Our usual direct wave, partially transmitted, partially reflected. Again, two waves on the side. I labeled them as creeping waves, but probably that is a mix of side reflections and creeping waves. Reflection from the underside starts with positive, polarity inversion. And then other two reflections from the side, from the corners. In a real radiogram, direct wave negative, top surface of the arch negative, positive, very weak. I can see it, I don't know if you can from your screen. And two hyperbolas. Before we had the two hyperbola branches. Now we have two full hyperbolas. Again, here it looks that it starts with positive, so another apparent polarity inversion. So from what we learned so far, now let's have a look at a real radiogram. This is a scan collected on a concrete beam, on the side of a concrete beam. So what we see here are link bars, 1, 2, 3, and there is a fourth layer here. And this is the other side, the back face of the beam. It is an interface concrete air, something air, so we shouldn't have a polarity inversion. The direct wave starts with positive, apparently here starts with negative, so we have a polarity inversion. But let's have a look at an A scan. So direct wave, positive, negative, positive. What is the dielectric contrast with metal? The dielectric of something metallic is difficult to assess because it strongly depends on the frequency used, and that is beyond the frequency, the GPR frequency range. That applies for any frequency. So because we don't know, theoretically, we can use the experience, we can just use the radiogram, and we see that the reinforcement starts with negative. So metal, at least this metal fissure, causes a polarity inversion. So it starts with negative. Second layer, third layer. This one looks that it starts with negative. Instead, it starts with positive. It is very weak, almost close to zero, but it is there. Why the negative looks more prominent then? We can say that it is because of the attenuation, but we can also say that the fourth layer of reinforcement, the one that is not visible, it is actually visible where the two hyperbolas cross each other. So here we have an example, here we have another example, and the other example is here. We just see the crossing point of this missing layer of reinforcement. And that constructive interference, probably in this case, amplifies more the negative band rather than the positive one. Although here, in this case, a bit of positive is visible. It might depend where we take our ray scan, obviously. Then the second case, more for a circle. This is an empty pipe, 600 mil diameter. Let's have a look at the eye scan. So, direct wave starts with positive. Top of the circle, no inversion. It should start with positive, but there is a prominent negative. But the positive is here. It is a sort of halo around the hyperbola. It is there. Bottom of the pipe, we should have a polarity inversion, theoretically, but we saw that we don't have it. But the negative is still prominent here. I start with positive. Again, very weak, not prominent, but it is there. Or probably only if we check an A scan rather than the radiogram. This is an example of square. This is a room hidden below a car park. So this this layer is the layer of asphalt, essentially. Then we have reinforced concrete, we see the bars. Then we have the ceiling of the room and the floor. We check our ray scan. Direct wave starts with positive. Here there is a mix between the reflection from the ceiling and the reinforcement, but we can see that there is still a positive, so somehow. Here we should have a polarity inversion, and that's what we have. It starts with negative. And we have also the two hyperbola branches, and we say that they should be as per the direct wave. They both start with positive. Fourth one. This is a scan collected on a bridge above the Thames. So this is one of the arches of the bridge. So let's check the eye scan. Direct wave positive, negative, positive, starts with positive. Top of the arch, I mean arch intrados, starts with positive, we can see here, and that is what we should be. We shouldn't have an inversion. This is the surface of the water, and this is, well, we should have two hyperbolas, but probably they are too close each other with only one below. Those are the reflections from the corners, these two. The reflection from the water starts with negative. It is again a sort of halo. Also, here we have a mess of signal, a chaotic pattern. So it is difficult, really difficult to assess, but using an A scan, we can have a better luck, and we see that we have a polarity inversion. And these two hyperbolas on the side, looks one, they are as per the direct wave. Okay. So from what we see so far, we can also check if polarity inversion can be used, or the polarity in general, can be used to understand multiples in the signal. So if we think about a slow material embedded within a fast material, the reflection from the top is fast to slow, so we have a polarity inversion. Its multiple, assuming that this interface doesn't do anything, is multiple will be inverted twice, so the signal, the polarity of the signal will be restored as per the direct wave. So the first multiple is as per the direct wave. The interface, the bottom interface, no inversion because it is slow to fast. And the same for its multiple, there is never an inversion here. In the opposite case, if we have a fast material embedded within a slow material, so slow to fast, no inversion, and the same for its multiple. Fast to slow inversion, its multiple, it is inverted 3 times, 1 here, 1 here, and 1 here. So at the end we have a polarity inversion. So we can see the difference between, and the analogies as well, between the two cases. So if we look at this one and we try to apply it to our data, let's go back to our room. We see how it should be. If we extend our time window, we see the multiple as well. So according to this sketch, the multiple should be inverted as well, polarity inversion, and that's what we have here. Why I'm showing this? This is obvious that it's a multiple, but I think I said the same last year. I saw radagrams like this interpreted as a room on top of another room, or a grave on top of another grave. I mean, interpreting multiples as real objects rather than multiples artifacts. If we apply the same sketch to our arch, here we have the two multiples. The first one is the multiple from the water, and the second one is the multiple from the reflection, from the corner reflections. So according to this sketch, we should have the same polarities that we see here. Instead, we have the opposite. Why? This sketch shows layer, so horizontal lines. Here we don't have a horizontal line because this is an arch. And we need to think what an arch is doing. When a wave propagates through the arch, reaches the underside, is reflected back, and we have a polarity inversion. This wave will be reflected back by the arch from the inside, but this is like a circle. And we saw that for circle, we don't have a polarity inversion. And that's what we have back. It will be inverted here, and this is what we will receive. And that's why this reflection has the same polarity as per the direct wave. This is, of course, says to us that polarity depends on the shape, and that's what we saw with the circles. But also, we need to remember that the first property of a multiple is that it appears at a specific time, a time that is a multiple of this time. The polarity is a secondary property, it's not the first one that we should look at. So now we can answer this question: do voids cause polarity inversion? And the answer is yes, but only at their backface or underside, depending on their shape and geometry. Apparently also at the top surface, but that is an effect of the attenuation. It's not a real polarity inversion. And also we need to remember, we need to note that when we go for a polarity analysis, we need to check the data, our signal, against a fixed and objective reference, and that reference is the direct wave. It is not another object in the radargram, because if we do so, we will never know which one is actually inverted. Not all the commercial antennas record the direct wave, and you can check by lifting your antenna from the ground and recording the floor surface. If the reflection has the same polarity as per your direct wave, it means that it's not a direct wave. That is normal for some antenna because it depends how they are built. And the waves, the first wave that they record is a mix of an interference of other waves. There is nothing wrong with that. It is just something that we may need to check if we want to go for a polarity analysis. Sometimes A scans are much more useful than B scans for a polarity analysis, but in any case, this kind of analysis can be done only when we have very good data, crystal clear data. If we have a lot of noise, a lot of scattering, probably any kind of polarity analysis will give us ambiguous answers. So now we have another question. What do we do for voids? When we go for a survey, any kind of survey, of course, the first question is, what are we looking for? What is our target? If we translate it into GPR word for voids, this is our target. But by voids, we may mean tunnels. We may look for sinkholes. We may look for defects. What kind of defects? Delaminations. Then we have cracks. Then graves, they can be void. There are also voids that are on purpose. And there are filled-in voids, so there is no air inside. Because they are different objects, how can we expect them to behave in the same way just because we call them a void? Each of them will be in a different context. And that is our main question. What is your context? What are you scanning? Where are you scanning? Let's have a look again at the real radargrams now. This is a radargram collected on a slab. Another feature that we can see typical of voids is ringing. It doesn't always happen, but it may happen. And I may think that I'm running on something, on a tunnel. This is a low frequency antenna. If instead, if I don't want to jump on conclusions and I look around when I am on site, I will see that there are other objects that can explain better my data. Here we have a metal duct that is just above my antenna, and its shape, we see that here the signal bends downward, and here the metal duct bends upward. The shape can explain better the data. Also, I have other scans, and I can see where this reflection appears or disappears in the data. And also, if I convert the depth scale that I didn't put on purpose, using the dielectric of air, I will see that this depth this depth will match this height. So where is the void here? The void is right below the slab, right below the reinforcement. Can I see it with this antenna? No. I know it because I had another antenna on site, higher frequency, I can see better details, but also because before scanning, before turning GPR on, I go around my site, I check what I have to scan. Sometimes I am lucky, I find areas where I can get many more details, I can see exactly what I'm scanning. This is another scan on a slab in a warehouse, where the slab basically sunk to the center of the warehouse. It was cracked around the perimeter, and the purpose of the survey was to find the voids below the slab. This is a low frequency antenna. We can see the reinforcing bars. Probably we see some layering here, but I don't see anything else. If I extend my time window, I see something that looks perfect to explain a slab thinking this surface here. But again, before jumping to conclusions, I look around again. I should do before scanning, not after. And I see that this reflection actually is the shape of the roof. And these three hyperbolas with a velocity of 0.3, they tell me straight away that these waves propagated through air and not through a void, just air. So why the slab sunk? Were there voids? We didn't see much with GPR. We saw some reflections just around the perimeter, but probably because the slab slightly detached from the ground. The problem was that the slab was designed to be a ground-bearing slab, but the ground was not strong enough to bear the slab. That's why it cracked and sunk. Here, this is a precast plank. We have 6 hollow cores, so structural voids. And this is how they look like in GPR data. We see the bars, these bars here, the sharp hyperbolas. They start with black, and we see the voids here. They start with positive. Okay. It happens that precast planks are modified. Every other hollow core is filled in with concrete, and there is a bar inserted in the middle, just to give additional strength. This is a normal procedure. The problem is when the precast planks crack. And this is why we did a GPR survey to try to find the cause of 30 or 40 precast planks cracked and supported to stay in place. And this is what I get in one of the scans. We see empty, filled in, empty, filled in, empty, maybe, actually partially filled in, and then filled in. So instead of, we can see that there is already a problem because we should have 3 filled in hollow cores. Here we have more, and one is with something wrong anyway. We don't have reinforcing bars because it should be one in the middle, maybe it's this one, we don't know, and one here. But also we see that there are voids. Where are these voids apart from these two? We have one reflection here and one reflection here. They start with black, apparently, but they should start with a white, with the positive, because here we have a reference. These two hollow cores were just partially filled in, and that's why we have an air gap. They actually start with positive, so there is no polarity inversion because there is a faint positive on top of it. So why we have a prominent negative? Because probably in these two cases, the air gap was too small for this frequency, for this wavelength, that the top and bottom reflections of the air gap partially interfered constructively each other, and they amplified the second and the third bands of the wavelet, but not the first. And then here we have layers. Let's just check the polarity. The direct wave starts with a positive. Then we have another layer that starts with positive. So we are moving from slow to fast. Fast, of course, doesn't mean empty. It means simply faster. And then we have another interface that it starts with the negative, a very tiny negative, just trust me. You cannot see it, but it is in this way. So can we assume that the layer in the middle is empty or anyway with a faster material? If we know what we are scanning, we don't have any problem with that. And this is a cavity wall. So we have brick layer, cavity, and brick layer. But if I don't know that is a cavity wall, what should I do? Here we have an hyperbola, very wide hyperbola. Here we have another one. And they fit the velocity of 0.2425, which is not 0.23. But that is enough for me to say that this is a cavity, because I would never have a 0.3, but just something less, because this is an average. The wave traveled before in a solid material. If I don't have an hyperbola to check, what can I do? Apart, again, checking what I'm scanning, because I can always find some information. I can do a CMP survey. That probably would be too much for this kind of surveys, but it is an option. That will give me a velocity profile, and from there I can get what is what in somehow. Here we have a concrete slab, top reinforcement, bottom reinforcement, underside, and then we have ground. In this scan, there is a void. Here we have, it's not this one because this is a metal duct protecting some cables, and the void is here. We don't see it, but it's there. And we know because if we use a polarization, if we rotate our antenna by 90 degrees, all the reinforcement will be almost gone. And what is not metallic, or not reinforcement at least, will show up. This is a plastic pipe. If I can use the polarity, but probably I will get confused with the polarity. But again, because I know what I scanned, I know what I was looking for, I know that this is a plastic pipe. It is empty, obviously. What is this? How many times people ask this question when we are scanning and they want us to give an answer immediately? This is a resistivity tomography, something different from GPR, but still geophysics. So here we have something resistive on the left-hand side, something conductive, and a resistive layer on top. Can I say what these two objects are? Is this a fault separating them? No. This is a frequency spectrum coming from a microtremor seismic analysis. And the frequency peaks that we see here indicate the boundary between geological strata. So we have 1, 2, and 3 strata. Can I say what they are? This is a radiogram. We can be more familiar with it, and we can attempt an interpretation, because we see a lot of small hyperbolas, maybe reinforcement, and then high amplitude reflections, maybe a void, maybe something like that. Another radiogram. Here it looks even simpler, because we see top and bottom reinforcement and underside of something, so it could be a slab, a concrete slab. For these two objects, for these two methods, it is evident that without a context, we cannot say anything apart of what we see in the figures. For GPR, sometimes it looks that it is less evident that we need the context to give an explanation of any sort. But actually, GPR is still a geophysical method. And when we provide an interpretation, apart from the fact that we take responsibilities for that, we need to be sure about what we are talking about, or at least we need to know what we are talking about. So to come back to this question, this is a numerical model that I built, so it's nothing. I just gave random numbers of resistivity, and this is what I got inverting. Probably I didn't do a good inversion as well. This is taken from this article, and this is a boundary between 3 meters of clay and a strata made of sand. And this one is the bedrock, is a sandstone, if I remember well. This again is nothing, because it is a simulation I made 3 years ago. These are not reinforcing bars. These are small void, circulars. And this is just an interface with a strong dielectric contrast. It is not a void. And this one, I said it is a slab, but instead it's a wall. Doesn't change much, or it does, it depends. So what should we do then in general? We should do what we always do, any kind of survey. We need to know the purpose and the context, because voids are not always the same. What kind of voids are we looking for? Once we know them, we plan our survey accordingly. The first parameter, at least for me, scan spacing, antenna frequency, obviously, a time window. We don't want to cut the signal. And then synergy. It was said in the previous presentation, who said that the GPR is the best method for any circumstances. We know that for concrete, ultrasounds are better in detecting defects, voids, rather than the GPR, especially if we are talking about small voids. We know that we can't always apply GPR. Maybe resistivity can be a better option if we are talking about very big voids, geological voids, sinkholes. What we shouldn't do is going forward with the preconceptions. Voids start with the negative band is a preconception. We don't go for generalizations. Sometimes some statements are true, but probably they are not always true. Because if we do that, what we get is that we make the method inapplicable, not credible, and useless. And that is the end of the presentation. I hope you enjoyed it. And thanks again for inviting me for the second year.
Davide, thank you so much. I really appreciate it. I'm sure everybody got a lot out of it, like folks did last year. Please put in the comments, questions that you have for Davide. We don't have any in there yet, but my guess is that people were focused on the detail that you were providing. But now we have some coming in. So please definitely throw some questions into the comments for Davide. So he said here, Layla says, thanks for the presentation. Her question, or his question is, what software you use for numerical modeling? Do you determine positive and negative polarity based on the sign R in reflection coefficient formula? So I want to go one by one then, because you got a few questions here. What software are you using for the numerical modeling, David?
I use the GPR Max because I can design what I need quite easily. It is easy to represent to plot the results in reflex. I can also use a reflex. There is a module for that. Of course, GPR Max is available for free. I remember for reflex, it's a bit more complicated to create the numerical models, but still the quality is the same. In terms of formula, the right one is the one that starts with the epsilon R1 at the numerator. So it is the second one that I show in the first slide.
Got it. And so their next question is, you determined positive and negative polarity based on sign of R in reflection coefficient formula. So when R is negative, you have a polarity inversion. I presented two formulas for R, that in the denominator there is epsilon 1 at first, and then the other formula with epsilon 1 at second, which formula is correct. And I think your sort of point was that they're both correct depending on the orientations of the antennas. That's true?
No, the formula that is correct is the one that starts with the epsilon R1. You can find both on the internet just as an error propagating around the articles.
Got it. All right. Any final questions? David took it to his time limit. But if you have any other questions, we got about 1 minute left for folks to ask. But Davide, thank you again. We really appreciate it. We've got a number of requests into the comments already for people who want to, revisit and review your presentation. Again, it's obviously so packed with information. It's hard to take all of it in in the first go around.
Yeah.
But I think a lot of folks just get so much out of the detail and sort of the ideas of, one thing that I thought was obviously really interesting is, we all know various ways to try to identify airwaves. But the way that you break it down, isn't just sort of character and velocity, but, using sort of multiple different variables in the response to identify them, I think is important. And I think it's a message that, has to go out to all sort of professionals, right? That there's, it's easy to become complacent, but if you want to be a professional and you want to be good at what you do, to continue to push and, add sort of tools to your toolkit. And I think that this presentation, helps people sort of see that there's more out there that they can be doing on an analytical level, project by project, to sort of distinguish, the quality of the work that they're doing in the future compared to what they're doing now. So thank you again, really appreciate it.
Yeah.
And
Thank you.
yeah, and we'll go on to the next presentation. So actually the next presentation is it's my presentation with Sean McConnell and Andrew Watson. Let's see, unfortunately I couldn't attend. Are we going to receive recordings of the presentations
Can you hear me, Dan?
today? The answer is yes, you will. So let me try to go ahead and share.
Can you see me, Dan?
Let's see.
We can see you, Sean. Yes.
We can see you. The world can see you, Sean. Let's see, screen or window. Let me try to do this here. Let me see if this works. Bear with me. Let's see if this works. Can everybody see the presentation?
We see another video of Sean.
Another
Yes.
video. Oh man,
Getting
2 videos of
overwhelming.
Sean. Lucky you. Let's see here. So I'll stop sharing. I can try one more time here.
There we go.
And what about now?
That looks good.
Can folks see the presentation?
Looks good.
Okay. So, this is a lot of these data that we're going to show now are collaborations that we've done with folks, a number of them with Andrew Watson over at Subsurface Mapping Solutions, who participated in constructing this presentation. And, in this case, the title of our presentation is Exploring the Diverse Applications of Multi-Channel GPR. And, we've sort of obviously recognized is MCGPR has been becoming much more popular in the professional space for ground penetrating radar services and geophysical services in general, including SUP. And we are going to show some utility and subsurface infrastructure data, but sort of the point here is you can get really creative now with multi-channel GPR, and we'll explore a few more applications of it. It's going to go pretty quick. We have a lot of images to show, but we kind of want to just explore this, diversity of applications that multi-channel GPR can be used for. So I'll sort of let Sean kick it off with mapping utilities and other buried infrastructure, and I'll kind of come in again in a moment.
Okay, sounds good. Let's fire it up.
So Sean, can you see the slides?
I can see the slides.
All right, go ahead.
Can you start the slideshow?
Yep.
Okay. Can you flip to the next one? I'm still seeing the title screen.
Are you still seeing the title screen?
Yes, it might be frozen up.
Okay, so maybe is this the way to do it? You see that?
Yeah, that works.
Okay,
Okay.
so we'll do it this way.
That'll work. Okay, so we use multi-channel GPR for a variety of applications. Probably the most popular thing that we're seeing is for mapping buried utilities and infrastructure, you know, pipe location and mapping sort of a thing. So what you see here is our larger vehicle mounted array, which is the Stream Up, and then next to it is the Stream DP. Those are both relatively young systems presented by IDS Geosystems. And for in-house, that's what we tend to work, although you'll see from our data sets, we use a lot of different brands. And in general, I think that multi-channel arrays are becoming very popular, especially in America and in Europe. Go ahead. Okay, and here we have one of Andrew Watson's data sets from Australia, and you can see that multi-channel arrays are very good when you're dealing with very, very dense environments. So when you have a lot of pipes really stacked on top of each other, this can be a very complicated thing to try and do with a single channel antenna because you're trying to look at one profile at a time and then walk next to it and look at another profile. And when you're getting just 12 hyperbolas on top of each other, it can be very hard to tell lines that are going diagonally across other lines, that sort of a thing. And so from a 3D perspective, doing multi-channel GPR allows you to make much more complex time slices, much tighter image resolution. And so it's better for complicated environments with lots and lots of features. If we can go to the next one. So this is what that information looks like as we're drawing it in the computer. So this is in a 3D view, and the lines that you're seeing that are teal and purple are, of course, ones that our analysts are drawing as the project is going on. And you can see they have some of the profiles and some of the time slices projected at the same time, and they're going in and they're mapping these things in the profiles as they see them. And in this case, I think we were using a two-color palette for lines that we had very high confidence in and lines that were lower confidence but worthy of being flagged. So you'll see what we call high prob and low prob. Now let's go to the next one. Here we are continuing the same project, and you can see this is the stream DP data. And if you kind of look at the bottom of the image, you can see all those little gray lines. Those are the individual tracks of each antenna. And in this case, the antenna separation is every 4 inches. And that's very, very useful when you're doing things through rebar and places like that, because a lot of times one antenna can be just right on top of a piece of like transverse rebar, and so it just won't see very much beneath it at all. But the next channel over, which is only 4 inches away, will have a good clean image. And so you have a lot of profiles to pick through. You can kind of manage looking around things and through things that are very difficult areas to see. And so you can open these up and then connect your lines across them, which is what's going on in this image. Here we have, this is a very different data set. This was done at a gas station. And this was actually, I think, the first thing we ever did when we got our new Stream DP in the office is we took it out, we ran it at the gas station across the street. But what we found is that the top-down imagery, because of that resolution, gives you a really good feel for the shape of things and how they're interconnected. And so as we're looking at this one, there's a few images that are going to go to different depths. So you're seeing here 15 centimeters below surface. You can see some tanks and you can see some lines that are feeding those. And this image is going to change wildly because there are just layers of different utilities. And doing this in 3D is much, much simpler than trying to do this sort of thing, just marking hyperbolas with spray paint out in the field. Makes a much more complicated job feel very simple. Dan, if you could show us a couple more. Yep, so here we are going down, and you can see a series of lines coming in from the southwest, heading towards the tanks, and you can see some more kind of features all around. And this is pretty much raw data. I mean, it's been image processed, but there's no drawings here. This is just what the lines look like from the radar data itself. And so the time slices themselves are very, very good at separating individual signatures. And so you'll see a lot of clustered lines here because it's not a blurry image. There just are many pipes side by side in some of these channels. And here we go, dropping down further, you can see kind of the overall network of pipes that are feeding all these different underground storage tanks filled with gasoline and diesel. They're 73 centimeters below surface, and they're still imaging, very, very clean. And this one we put in as well. This is live in the field. We're using a hot iron color set, which is an unusual choice for us. But this is what it actually looked like on board the machine. In fact, you can see there's kind of a little yellow square there. That's the GPS indicator of where we were standing while we were out there looking at it. And so you could make out a lot of the tanks, a lot of lines and things like that live in the field. So you have kind of a top-down quick perspective to show customers on site and to judge how well things are working from a processing standpoint. And then when you bring it back and do it on computers, you can clean it up and draw the pipes and export them formally.
All right, you want to take this one, and then I'll take the last.
Okay, this is another one we did with Andrew Watson, which is mapping wombat burrows, which is kind of an interesting situation. So out in Australia, there's a number of endangered species, of course, and we were concerned about is the northern hairy-nosed wombat, which is a critically endangered species. So there's a lot of work going on to try and preserve the habitats of this creature and to understand those habitats for the sakes of being able to protect them. And these are a burrowing species, and we learned quite a bit about wombats doing this because although the creature itself is maybe that big, the burrows that these things can create are tremendous, and they're very long and very complicated networks, and not much was known about them. And so being able to investigate that non-destructively with radar is a very powerful tool for these and other burrowing species where you can investigate very complicated things going on underneath the ground. And in this case, you'll see very shortly, it's not just that the wombat burrows are a target, but the reason you want something like multi-channel is because they're in an area with a lot of tree roots and other problems that make it very hard to separate your target from things that are not your target. And that's where multi-channel really starts to shine because of the data density. So here you can see Andrew Watson's team with a stream DP. They're pushing it over. That huge hole is a wombat burrow. That's these little creatures live in there, and they kind of wind all over. And you can see them at an entrance, but it's very hard to get good maps of these before GPR at least. And so out there in the field, because there's so many trees, and this is actually a pretty clear spot. That's probably why they took a photo there. It's very hard to maneuver around. You can't do straight lines. You're not going to be able to do a traditional rectangular grid. So we need modern software where you're integrating something like a GPS and you're able to do 3D imagery while doing curvy, windy surveys in between trees, which is pretty complicated stuff that would have been very, very hard to do just 5 or 6 years ago.
Yeah.
So you can see the GPS tracks. They're sort of spirals. It looks kind of like a kid drew it with a crayon. And that's Andrew Watson's team did actually a very good job of getting coverage in a very, very difficult situation. But when you're working in a forest and there's big roots and big holes, it's very hard to get anything like a rectangular grid. And so the game plan with a lot of these multi-channel systems is that you can turn on your GPS mode and just get coverage going any direction you can because you have so much information density and such tight little interpolations and search radius when you're creating these top-down images that you can get away with some techniques that you just couldn't do with other systems. So here we go. This is what the data kind of looks like as we were processing it. And a lot of these long red lines that at first me and Bobby were like, man, there's a million wombat burrows. And we flagged all these and sent them to Andrew Watson and his team. And they said, a lot of these are tree roots. And we discovered very quickly that not everything that's a long, bright red signature in those top-down slices is a wombat burrow. And so this is where multi-channel really starts to shine, is when you have that very high complexity and a lot of things going on at once, you can separate your targets and draw out just the things that you need to find. So this is an idea, and actually it follows David's excellent presentation very well, where we're doing more than just looking for hyperbolas and tagging them. You're really looking at the features themselves and distinguishing them based on their characteristics from the signal. And in this case, you see that double hyperbola, which is a result of there being air. So this is a hollow tunnel like the animal is living in it. And as the signal is coming through, you're getting a reflection off of the top of the burrow, and it's going through open air and then hitting the bottom of the burrow and giving you a second hyperbola. And that double shape became, in this case, the telltale sign of a wombat burrow versus a tree root. Here we are. And so this is a couple examples of what those look like. And we're now looking at
sorry about
top.
that.
Yeah.
Go ahead.
So the width of the hyperbolas will change quite a bit because the width of the wombat burrows changes, but also because our angles going across these is going to change. So you're not always getting a perfectly clean cross-cut transect like you would try to do with pipes. These are targets that are winding and they're very hard to predict underneath you. But that double shape characteristic, once you've trained your eyes to find it, it's not that hard. And so your confidence, once you understand the data set, is actually very high. So you can map these things and really be pretty certain of where you're drawing things that you've done a good job. And so here we are drawing these in the 3D. So those red marks, I don't remember if those are wombat burrows. No, I think those are trees. And then there's a pair of red lines here at the bottom of the yellow pipe. And that's yeah, thank you, Dan. That's where a wombat burrow was observed. And so you can see how our signature follows that wombat burrow and it sort of winds around left and right. You'll see in some future images, they also do a lot of up and down behavior. They're not, a straight line like a pipe is. But you can follow them with a very high degree of confidence, even in a very complicated environment. And so here we go. This is a great example. So you can see how it rises to meet the surface where there's a wombat burrow captured in our, I don't remember if it was a satellite image or a drone GPS image, but you can see the wombat burrow highlighted with a white box and then a little yellow tube that snakes around, and that's the actual shape of the burrow underground. And this is, very high confidence work because the signatures are actually very clean, despite the fact if you look at the GPS tracks, they were winding around all over through the Australian brush. Yeah, and I love this image. This was being done in IQ maps, and you can see where they dropped away the ground just to kind of give people an understanding of what it would look like if you could see the tree roots, which in this case are green, versus the wombat burrows in yellow. You can see how they intersect and they combine, and that's part of the maybe social behavior of wombats. And this is the sort of thing that biologists and scientists are going to want to know a lot about. And so they can make inferences based off of the GPR findings about how these communities are being structured. And also if they wanted to go in there and say, look at that chain, which is marked in brown, that might be like somewhere where wombats give birth or something, they would know where to find exactly that thing and could maybe design an investigation to send a probe into there and watch the wombats with minimal disruption of the endangered species.
Okay, so I'll sort of step in now, and everyone can still see the presentation. Does somebody verify?
I see it.
You can see it.
Okay, so the next one we did with Andrew, again, this has been a really great collaboration where we've been able to work together with other professionals and solve some really intriguing problems, was detection of a seawall. And this seawall, obviously was used to protect the beachfront itself, and they were going in, or the sort of idea was to potentially mitigate some damage or refurbish the seawall. And the real question was, where was it? Was this sort of high rise over here, the wall, or were these just dunes built up over time, or what was the situation? And so what was nice in this case is we were able to get drawings of the seawall, or what was supposed to be the construction sort of makeup of it. And it was a sort of a rock, gravel and sand, built wall, and with a sort of a clay underpinning there. And so it allowed us to sort of try to make expectations of what the GPR responses, should look like. And, when you have sort of a compaction of rock and pebbles, then you can sort of predict, right, that you should see some sort of scatter or sort of these micro reflections off of those, as opposed to some other sort of response. And so basically, and we'll show you the entire beach in a second, but here's sort of what we were seeing, right? And at first, it was a little difficult to try to define, well, what's what? But once we sort of zeroed in on, okay, there's a geological layering here from the beach compared to areas that had these sort of scattered reflection events. As you can see under the blue, we were able to sort of detail out where those scattered reflection events were occurring. And so this was definitely a unique application, on the beach. The other thing that was interesting was, I think under sort of normal circumstances in the past, a single channel tow kit to drag on a beach would have probably been an ideal deployment method. But with the way that these carts are now being built, in this case it was a Stream DP as you saw, they're light enough where you can actually push those in conditions that were previously inaccessible by multi-channel. And so having sort of the multi-channel gave us a lot of examples. The problem sometimes is, one pull or two or three pulls across an area, you have limited sampling to make interpretations off of. The benefit of a multi-channel system here is you do the same 3 passes, but you've got 90 transects that you can sift through to try and make your interpretations of the location and size of these things. So here was just a really good example of where you can sort of see the delineated wall and then sort of the underpinning, of that rock and gravel construction. Here's a few more examples. What's nice about these is they're not nearly as clear as the first one. So in the example to the left, you can see the entire subsurface is far more messy, but we sort of identify in aggregation of those higher amplitude, smaller reflection responses to the to the right hand side there, and because that would be to the east, and we were able to sort of pinpoint that, and then with the 90 transects right across 3 pushes, 90 lines across profiles across 3 transect pushes, you're able to sort of follow that out. And so line to line to line, it's easier to sort of make interpretations that you feel confident about as compared to a lower sampling rate of profiles. Again, over here, you can see most of this profile, right, was a shorter profile on the right-hand side. A lot of this underneath seems to be a part of that construction. We may have sort of extended a little bit further. It does get a little bit dicey, to use a scientific term, on the right-hand side there, on the east, but on the west, you can see that that rise that's expected for the wall and those scattered responses that are aggregated underneath that blue line. And so here's the entire beachfront that was investigated, and what we were able to identify is, is the wall built in a completely linear pattern across the beach, or was the build out of it not consistent across the entire beach? And obviously, what you can see is in the identification here, across the entire beachfront, it was not fully consistent. The red line there that moves across from east to west is the expected location of the wall. And in some of the cases, the interpretations conform to that expected location, and in other lines, there's obviously a shift, towards the actual water itself. And so this really helped the Andrews customers pinpoint locations, right, for targeted investigation and refurbishment of this seawall to continue to protect this entire beachfront. Another example, right, to use multi-channel GPR as an archaeological prospection. Obviously, as Stephen Twist had mentioned the first go around, archaeological sites are some of the ones that he'd most prefer to revisit with multi-channel. What we have here is a situation where there was a site that we've had investigated for years, actually, in both, kind of traditional geophysics as well as excavation to follow that up. And, we ended up having a very short period of time where the archaeologists that we were working with from coming down from Wisconsin, University in Wisconsin, we only had a day. And so we ended up taking out the multi-channel, try to cover some space within that day and help answer some additional questions to support what they were doing. It was located in northern Georgia. It's right on the Etowah River, and you can see where the site location comes in. There's a kind of a meandering river over there, Etowah River in Dawsonville, Georgia. And here's some of the features that we had excavated out previously in earlier years in a specific sort of section. And we found multiple buildings. And on the left-hand side, you can see that's a a post hole, and so there was a mold from a wooden post. This site specifically dated primarily to the Woodland and Mississippian period. So you're talking, somewhere around, from sort of 1 AD to 1000 AD. And they were primarily wooden structures that were constructed during those periods, and they would be post holes and then sort of a wattle and daub wall. And so they're weaving, twigs in between these larger posts, and then padding those with clay and then baking that in the sun for a really good structure. And so we were able to identify from previous geophysics some of these, a lot of these post holes in sort of patterns that were consistent with buildings. In one of the buildings, we found this feature, which was really interesting. It was just filled with rock right in this feature, and you can see underneath, there was a burn layer, and there's a sort of thin layer of ash right there, and we were able to take that and get the site dated using radiocarbon dates. So some really neat features. There's probably a central feature to that building, sort of coordinating, activity. And so in this case, here's some of the examples that we have. And so these dots, these blue dots, and then this yellow one, just highlight yellow because it's showing you the box. These were areas where these professors were coming to do tests on the alluvial deposits, because it was right next to the Etowah River, and sort of trying to understand the alluvial deposits, but also what other archaeological remains were there that were near those features that we've uncovered in the past, and were there any that were further away. And it was in a pretty large field, agricultural field, where these were. And so here's a profile view that you can see some subsurface responses, indicative of potentially archaeological features. Also, though, there were animal burrows across this field as well. And but we got some patterning, right? And so you can see here, that there's some patterning, and several of these structures that we had uncovered already were square structures and rectangular structures. And some of these high amplitude distributions conform to that geometry. Of course, this one right here also has a high amplitude response, right in the center as well, which may have been some other feature, such as this one or something similar that we had found in the past. As we continue to sort of cover some space here, there were additional patterning. Both of these images that I'm showing you here, this one as well as this one, were near the river and near the concentrations of excavated archaeological remains from the past. And it does seem here that we continue to get some additional patterning in high amplitude responses, as well as potentially some internal features and potentially external features. I think that this faint ring is really interesting because you do see it in the data. And one of the questions when we first submitted it was, well, is that just where a tractor turned? And, of course, in this case, it's pretty shallow. Here, it's, just a foot below surface of 0.3 meters. But if you do look from the top down, the consistency of the geophysical response with the actual aerial photo, you see that ring complete itself in a darker vegetation pattern. That matches with the half a ring that we had recorded with the GPR. So this I thought was another really sort of interesting, find. And what we're potentially getting here then are buildings in different shapes, and that may be because different functionality, or it may be because they're used at different periods of time, or some other interpretation. What was really interesting was we found that in the middle of this field there was little identified, sort of through just some sampling over here, obviously, but the river is just on the other side of this tree line, just on the eastern side of this tree line, And the data I've been showing you is sort of in this area around, this garden where we couldn't get into, but sort of testing along that line that they were doing for alluvial, um, probing. We found that there's limited in the middle of the field, but we get then high concentrations of high amplitude reflections again, somewhat patterned further away. And this sort of has led to the potential for test excavations in this other area that has up until now gone unexcavated and untested other than through geophysics. And this is pretty deep. And so you have 1.2 meters here. As we go down further, there seems to be some additional patterning. It's more faint. That said, it's also 2.3 meters below surface now. And we're talking, Georgia clays and alluvial deposits all moist. And getting these depths with a 600 megahertz central frequency was pretty interesting to us. And so at least what this did was it helped identify rather quickly that there may be other locations in this field that should be subject to test excavations, not just the areas that had the high concentrations in the past. One final application, sort of before we wrap up, is bridge deck inspection. So this was another partnered investigation that we worked with GS Infrastructure on, where they were using 3D radar, now Contour. And by the way, as a shout out to Contour as one of our premium sponsors for GPR Congress. They've been along for the ride the entire time that we've done this, and we appreciate all that they do. And in this case, you have an air-launched step frequency continuous wave system that's being able to run at highway speeds. And in the case of GS Infrastructure, which now has a new name, and they also have infrared to combine that bridge inspection GPR data with another sensor, which obviously we saw the power of that in the first talk. And over here, I think what's interesting, and this gets back to what Stephen said, right, is safety. Safety and density. And Stephen said, he goes, well, look, you can do less with a person out there pulling a system on the road. In our case, on a bridge. But the benefit of having 20 some odd channels in this system and running at highway speeds and nobody outside is you get extremely high density data. I mean, we're talking 100, or 110 profiles, right, from, or I guess that would be even more. There's six transects here at 20 plus per transect. You're talking 110, 120 lines that you can look from with nobody getting out, and you can do it in a really short period of time and get a lot of information. And so the Examiner software, which this was processed in, gives you the functionality in order to make some quick interpretations about certain things that are critical. So for bridge deck analysis, these were done in Maryland. I'm going to show you two bridges from Maryland where the multi-channel, high-speed detection and then rapid turnaround of information is really helpful, because getting certain responses here, from the data is sort of a proxy for what's the condition of the bridge. And primarily what they're looking for are rebar cover, they're looking for bridge thickness, and they're looking for amplitude from rebar. And the idea here is, shallow rebar cover is sort of a predecessor to infection because it's more susceptible to problems as it's closer to the surface. And, if there are rebar that are corroding out and you're getting less steel, less surface area, that ultimately should result in lower amplitude responses. And so in this case, we have the distribution of bridge thickness, that's slab thickness, and you can see it's not totally consistent. There are some areas that are closer to about 0.8 feet, or about, I don't know, 20 centimeters ish for the folks elsewhere in the world. Here's an example where you get a little bit of thin thickness, and here's another example where you get some thin thickness as well, and other areas that are thicker. Here is rebar cover, and you actually find that where you're generally getting thinner slab thicknesses, you're getting shallower rebar cover. In some cases, just a few inches below surface. And so you have sort of this area here, sort of in general to the northeast, and sort of these, this area kind of isolated in the southwest. And then we're able to convert these just to amplitude analysis. And so what we found was actually, despite some of the thinner areas on the slab and some of the shallow cover, is there was an isolated incident here that was charged with additional investigation because it had far lower reflection amplitudes returning to the GPR. And we ended up inverting, right? So the hot color is actually low amplitude and the cold colors are high amplitudes. And so the point there is to highlight where there's low amplitudes, and that's what we did. And so here was one specific area. Whether or not it is corroded out, unknown, but it's certainly an area that's of interest for targeted additional investigations, whether that's other sensors such as half cell potentials, or with actually drilling in and verifying it. One other bridge here, again, areas that we have, obviously thinner slab thicknesses, which correspond with the roads that are going underneath, and then thicker slab thicknesses on the other sides of the roads that are going underneath. You get the same pattern here, where you're getting shallower cover in certain areas, which are somewhat correspond, but that not totally, with the thinner slab thicknesses. And then for amplitude responses, there were some, not as dramatic, but quite a bit of small patches that had low amplitude responses off of the rebar. And in this case, we suggested that they do additional investigations on this. And these data were actually processed, and I'll get a go. I saw him in the audience before, but Dominic Day participated in this project when we had done this with GS Infrastructure. So that's it. We thank you all so much, and we hope you got something out of it. We hope that you maybe found some other applications that you might never have thought of with multi-channel. And we're just super excited about this and sort of what can be done and the scale of what can be accomplished and the types of diversity of applications that we'll be able to evaluate. So I guess we'll take a couple questions. Let me just see here real quick. Okay, so we've got 7 minutes till break. So I'll scroll back through. Let's see. Let's see. I understand that the Stream DP is lightweight, but how well did it work pushing it through the beach sand? That'd be a question for Andrew Watson, who I don't know if he's on or not. He's obviously it's nighttime for him. But we've had. I'll put this question to Sean, who's pushed it around more sites than I have at this point. Sean, what's been your situation with rugged deployment?
Compared to all the other multi-channel platforms that I've used before, I really like the frame, the chassis on the DP, which is kind of the lowest tech part of the whole thing. But it has these quick detach wheels that are quite large. So you can put the wheels on it and suspend the antenna for towing it down roadways and smooth grass. But when you're in really loose sand or like we do a lot of cemetery work, and it's very hilly and undulating kind of grasslands, you can actually take two of the wheels off, and that way the whole antenna box just sits on the ground and it acts like a sled. And that works really well for the off-roading. It's really not hard to pull. And you can put ropes on it and pull it. It's pretty light system, so I think that works really well for us is to use rope.
Yeah, and that's something actually that Adam Cook also sort of alluded to, right? That you can pull it when you take the wheels off, of the system. Let's see. I'm jealous. I wonder if anomaly was exposed to higher moisture levels. Yeah, that's another point, right? Is the GPR data is remotely sensed, right? So we can sort of make assumptions about why is there a lower amplitude response, and does that lower amplitude response mean that it's corroded? It doesn't, right? It could just be that there's additional moisture in that particular area of the bridge, which is causing faster signal attenuation and strength reduction. And so when we get it back, it's just not recording as high of an amplitude. So it doesn't mean that it's corroded. However, right, additional moisture, either way, it would be a target for investigation, because concentrated moisture in a specific section of a bridge, if it's not corroded out now, would be probably the leading cause for future infection. And that would be where we'd suggest people investigate anyway, in those situations. But it was a good point there.
Oh, I like, my favorite thing about finding those concentrations of moisture levels, you can catch problems early sometimes. And I know one of our Canadian clients, we were really impressed her people by showing them where they were having drainage problems that would cause problems in the future, but they were able to kind of just do little fixes right away to prevent it from getting bad in the first place. And I think that's really where GPR is starting to shine, is in the preventative maintenance side of things.
Yep. All right. 3 questions from Davide. Said, have you ever been asked to estimate the volume of those animal tunnels? We haven't. Obviously, we were pretty surprised that you got the double hit. We usually don't see that. So, for example, in non-metallic air-filled pipes, we don't often see a double hit. The way that we would try to do that is to use the velocity in air and then recognize the time difference between the first and second hit, divided by the two-way travel time, and then try to sort of make that assumption. Unfortunately, we don't often get to do that. And in this case, we weren't asked to do that. It would be a cool thing to sort of go back and maybe do, as an academic exercise. But we have not been asked to do that. That's how we would do it. How do we calibrate the velocity for the bridge deck thickness and reinforcement depths? So we'll do it in 2 ways. Obviously, there's an estimate, which we're using a hyperbola matching function for the reinforcements that are being recorded inside the bridge. And so it allows us, the Examiner software gives you lots of function to do that. And so they're usually quite good estimates. But obviously, the better situation when we can get it is expose a bar and get some depths of those bars, so we can actually use physically measured depths. I don't know for those two exactly what we had done, but those are the 2 ways that we've done it in the past. Have you used a multi-channel system to collect CMP data? We haven't. I mean, it's a really interesting proposition to use it to get common midpoint information. I think the systems we have are a little bit too closed-ended. Unlike Steven's system, where he put that together with the SIR 10 and had multiple units that he can sort of get from it, and possibly get recording, from one transmitter on 3 separate. We haven't done it. I don't know if the software that we have allows us to do it. Lissandro, if you're out there, go ahead and code that in. But it would be great. I mean, it would be an excellent opportunity to get, an additional way to identify velocity and get maybe more accurate depth estimates going forward. So yeah, I mean, that's sort of the answer to the question. Let's see this one from Alan Viscara. Dr. McConnell did my whole dissertation mapping tree roots with the GPR. I'm a plant scientist. I would like to connect with you on this matter. Provide your email. Dr. Sean, there you go. It's in there. I see afterwards. If anyone wants to contact Sean, his email's in there.
Hey, I want to say, we probably had a theory. We haven't gotten a test yet, but with the tree roots, you can produce an ISO surface map, which you can do in GPR Slice and Geolytics in particular, where you can see the roots and they look like a 3D object, and you can do things to kind of tune it up and down. And so we've theorized that if you could expose a piece of root, we could adjust the Hilbert transform to be the size of the root at that location. And from that, we could then, the isometric image of the rest of the tree root site can pull a volume calculation. But nobody, to my knowledge, has ever done that before. But that's something, if you're doing that as a dissertation topic, that'd be something we'd want to talk about.
Yep. Any other questions? If not, we hope everybody had an excellent first part of the conference today. We get so excited doing this, and leading up to it every year. We get to, learn so much from everybody else out there as well. We appreciate everyone letting us present today. And we hope that we appreciate the first 2 presenters as well. I also want to say thank you so much to our sponsors, Contour, which makes multi-channel radar, and Geolytics, which is a super fantastic data processing software, are the premier sponsors. And here's a message from Contour before we run to lunch. Okay, everybody, welcome back from lunch. Excited for the afternoon. Before we go to our next presentation, which will be from Randy Bream, about investigating a cemetery, is we're going to have another commercial from our other premium sponsor, Geolytics. And I just want to say really quick, thank you to all of the sponsors: Contour Geolytics, Reveal over in New Zealand, AccuScan in New York, Screening Eagle, and HSC Pipeline Engineering. We appreciate everybody's support. Please go check out their websites, reach out to them for help. But a special big thank you, to our two premium sponsors, Contour and Geolytics. And I think we have then the other commercial for Geolytics. So pay attention.
Welcome to Geolytics, your solution for subsurface data analysis. Geolytics supports all GPR manufacturers' data formats with an intuitive drag-and-drop interface. Harness our automated processing features which analyze your data and suggest optimal processing parameters. Geolytics includes all GPR filters, giving you complete control over settings and processing sequencing. Make interpretations using either 3D slices or detailed 2D profiles, allowing for the construction of very complex subsurface models. You can seamlessly integrate additional data such as georeference site photos, drones or satellite imagery, CAD base maps, drill holes, and other geophysical data sets into the same 3D workspace. Exporting your results in various formats is easy. You can even create a link for stakeholders to view specific project elements. Try the platform for yourself and discover its capabilities.
All right, thank you so much. And again, if you saw there at the end, it looked like they're offering a free month of usage for Geolytics. The code, I guess they can pop right into the chat for people who can use at the Geolytics website. And so make sure that you check that out in the chat. Okay, so I'll hand it over without further ado to Randy. We're all looking forward to his presentation, and take it away.
Everybody can see this?
Yes.
Yep.
Perfect. Okay, so good morning, everyone. My name is Randy Brehm, and the title of my presentation is Chasing Ground Penetrating Radar Anomalies at the Saskatoon-Montana Cemetery. So this is a Microsoft Copilot AI generated. So I'm a little bit younger than this fellow, but not by much. So first, a brief introduction. I'm a professional geoscientist licensed in the province of Saskatchewan. I own and operate a small little consulting company called NS Geoimaging. So I began running GPR surveys back in 2009 in underground potash mines, mapping clay seams, which are a potential zone of failure in the mines. So like most things with GPR, it is always a tool for ensuring safety. My initial experience was with a 2 gigahertz horn antenna, where Brian Jones from GSSI fame gave a demonstration. Currently, my GPR work is above ground, either in geological or archaeological settings, and primarily in data processing and interpretation. So here's the agenda of the talk. So the initial scope of the survey, location, geology, background of the cemetery, and previous surveys at the cemetery. The bulk of the talk will be on the actual GPR surveys at the cemetery, some probable or possible interpretation of the anomalies, and some simple modeling. So the initial scope of the survey, the University of Saskatchewan, they have a geophysics department, and they requested a GPR demonstration for their annual field school in May. So there was 2 locations. The first was at the Nusahana Cemetery, and the other one was at an old landfill near the university. In conjunction with the GPR survey, there was a electrical resistivity tomography survey, ERT for short. And these are also run in adjacent to a row of headstones, and they did a couple of profiles. So we used a sensors and software 250 megahertz GPR antenna, and this was borrowed from the Saskatchewan Polytechnic Mine Engineering Technology Department. And so this was, well, not typically bare bone, but it was without an attached GPS receiver. And we set up a grid in the same location as one of the ERT profiles. Okay, site location. So the city of Saskatoon is in the Prairie Province of Saskatchewan. And for those who are watching this stateside, as a reference, it is 1,000 kilometers or 600 miles directly north of Denver, Colorado. So the city of Saskatoon is a quaint little city with a population of about 250,000 people. And there's a nice river called the South Saskatchewan, which originates from the Rockies. And it bisects the city into 2. Basically, there's the east and the west side. On the west side of the city, or on the east side of the city overlooking the river, is the Nutana Cemetery. And it is roughly about 5 kilometers southwest of the downtown core. Superficial geology. So the surface layer is typical of southern prairie provinces, which is a glacial-lacustrine plain deposit. And this means that the beds or layers are deposited during summer and winter cycles in a glacial lake. In the area of the cemetery, the surface layer is predominantly silty clay, and it extends to a depth of about 6 meters. On a side note, many people would refer to this as glacial clay or glacial till, and this is incorrect. Glacial till is a morainal deposit and is generally composed of gravel with a matrix of sand, clay, and silt. And glacial till are deposited by glacial ice, not by a glacial lake. The city of Saskatoon Nutana Cemetery. So it's about 5.6 hectares in size. It is a inactive cemetery and is designated as a municipal heritage property by the city of Saskatoon, and it's protected under the Heritage Properties Act. It is also known as a pioneer cemetery, and the first recorded burial was in 1884 and was interred overlooking the South Saskatchewan River. The last burial in the cemetery was in 1948. And this is an example of an open prairie cemetery, which means that there are no gates or fences, thus retaining its prairie landscape. Unfortunately, this means that there is potential for more vandalism within the cemetery. So there are 162 known interments in the cemetery, and after 1910, only burials that were allowed were those who already had purchased plots. Now, being so close to the river, it is subject to water erosion, and the hillside on the west edge of the cemetery adjacent to the river collapsed numerous times. The first in 1904, next in 1969, and in 1984. And these slumps or collapses, they caused damage to many graves. So they had to relocate a bunch of these graves, either to the east side of the cemetery or to the city's other cemetery. The GPR survey location is where numerous of these grave sites were relocated due to the slumping of the hillside. And these are now situated on the eastern end of the cemetery. According to a local historian that's well versed with the city of Saskatoon, the best guess is that they are relocated in 1904. This cemetery being close to the University of Saskatchewan, there were several geophysical surveys at the Nutana Cemetery. So in 2020, the University of Saskatchewan Anthropology Department, and they were involved in search for unmarked graves at the residential schools. They were initially practicing their techniques. So they used censored software, 500 megahertz GPR equipment, and also I know that they used single frequency domain EM, I believe was a Geonics EM38. In 2022, the University of Saskatchewan Geophysics Department went to the cemetery, and they were using electrical resistivity tomography to see if they could use this to map known grave locations. Okay, so we're getting into the actual surveys. So the very first survey, it was part of the Geophysics Field School for the University of Saskatchewan. We set up basically a grid. So the acquisition parameters were the line length was unidirectional at 31 meters long. I have no idea why we chose 31 meters, but that's just the way it was. Distance between each of the profile was 0.25 meters, a 2.5 centimeter step size, and the maximum depth was set at 3 meters using a velocity of 0.1 meters per nanosecond. Here we have visually the layout of the lines in Google Earth. So the survey consisted of 9 lines running south to north, and these were adjacent to a row of headstones and flush grave markers. Unfortunately, precise geospatial control was insufficient. Unfortunately, the H-stop values were elevated, so I think the best we could do was about a 2-meter accuracy, which is insufficient. Now, these lines were positioned using the flush grave markers as a reference, and these are easily identified on the radargrams, and I'll show you some displays later on. So on Google Earth, here we have some of these flush grave markers. So here are a few pictures of the Geophysics Field School in the cemetery. On the left is the ERT survey, and of course on the right is the GPR survey. For those who are unfamiliar with ERT surveys, we have a bunch of these stainless steel electrodes, and they have a pointy bit at the end. And these are inserted into the ground at a depth of approximately 20 centimeters, and they are evenly spaced at about 1 meter apart. So this is a general view of the headstones, and this is looking north. We can see some of the flush grave markers on here, and of course the headstones. We can see the ground conditions. It's not your pristine, lawn that you would see at some cemeteries. There's some hummocky bits and dry grass area, and also some dandelions. So the processing flow was fairly straightforward. So first of all, I aligned all the first arrivals, the signal saturation correction or DUO. I applied a full width background subtraction and some gain compensation. And then for the amplitude or depth slices, I applied a slope migration with a velocity of 0.08 meters per nanosecond, and also instantaneous amplitude. So here is the centermost profile. This has a profile length of 31 meters. The orientation, south is on the left-hand side and north is on the right. Not too much going on. It's not your typical expected grave site signatures in the cemetery. And these would obviously be hyperbolic-like events or indications of disturbed stratigraphy. This is all possible due to the ground conditions. We have a very hard silty clay. Again, the age of the burials are, they're about 120 years. And of course, we don't really know what the materials are to use to build the coffin. So it's likely some form of wood product. And I have placed the locations of the headstones and also the grave markers along the profile. So there are some features. So this is the most westerly line for this grid. So this is right adjacent to the row of headstones. We can see a water line to the south, and it images quite nicely in the depth slice. And in the center of the profile, we have these flush grave markers. So they actually give a nice response in the profiles and also in the amplitude slices. Now these markers are small granite blocks, and they're for size, they're probably a little bit larger than a loaf of bread. Okay, so due to the inaccuracy of the GPS coordinates, we decided to do a follow-up survey in July, and so we did ground penetrating radar and ERT. So we extended the grid eastward to capture a metal-topped observation monitoring well. Here it is right here. And we use this for better geospatial control. Again, we still didn't have GPS, but the nice thing is this monitoring well is easily identifiable on Google Earth, so we could position things nicely with using that as a reference. And there are some additional flush grave markers to the east. And we ran the GPR equipment over top of these. So this monitoring well, it has a metal top, so it rings nicely in the radar profile. And here we have the monitoring well, which is visible in Google Earth right here, and also a zoomed in display of the actual well. Okay, so here we have the second GPR survey layout in July. It consisted of two grids. The first to the west was very similar to the survey collected in May. So there were 12 lines running 45 meters. And so here's the first grid through here. The second grid, the lines were only 25 meters distance. Again, there was 12 of them. So same parameters, previous 0.25 meter profile spacing. And in the processing, we combine this into a single grid. Okay, so here we have a profile from the second grid. We can see the ringy appearance of the monitoring well. Again, we see the monitoring line and some of these flush grave markers. But actually, this is something else. This line did not go over top of these flush grave markers. So what are we actually observing? So here we have a amplitude slice. So this is a depth slice of 0.2 to 0.3 below ground surface. And we can clearly see these flush grave markers. So we can see the ones on the second grid and these ones over here on the first grid. Again, we have the monitoring or the water line and also the monitoring well. So this is a depth slice that's actually going a little bit shallower. And we see these interesting shallow rectangular truncated anomalies. And the reason they're truncated, we just didn't extend that survey far enough. And we see 4 of these, 1, 2, 3, 4. So side by side, we have the amplitude slice at a depth of 0.2 meters. And on the right-hand side, we see the depth slice at 0.3 meters. The one to the left, which is shallower, we have the rectangular truncated anomalies. And we do see kind of the initial appearance of these flush grave markers. And interestingly enough, we see that these things do align quite nicely. So let's look at some of the profiles through the data set, through the grid. So here we have 3 profiles, and they're each about 0.75 meters away from each other. So the very first one, this is going directly over the flush grave markers. And here we have the signature of the flush grave markers. Profile 3, this is going through the shallow rectangular anomalies through here. And halfway in between, we have profile 2, and we don't see not much at all. Of course, we have some fiducial marks when we're doing the survey. I was pressing the button on the DVL to record the instance where we went close to that flush grave marker. So I decided to display these profiles without background subtraction. And we see that these shallow rectangular anomalies are very, very subtle. So here we have the profile 1. This is going through the flush grave markers, and profile 3 through the anomalies, and we see that the signatures are of the 2 are completely different. So not everybody likes to look at variable density displays all the time, and I'm a big fan of looking at wiggle trace variable area displays. So here we have the same display zoomed in a little bit, and we can basically see some of the subtleties between either the flush grave markers, and my best guess is that we're actually capturing the base here. And for the shallow rectangular anomalies, it is completely different than what we see in profile 1. And zoomed in a little bit more. Here we have profile 1, and again profile 3, and this is the first of the anomalies going from south to north, and we can see that we have a trailing trough after the first arrival and appears to be lower frequency than for normal ground conditions. And then following the trough, we see a dim positive top-loaded doublet right through here. Okay, so how far do these rectangular anomalies extend to the east? This is always a common thing, you know, in geophysical or geological exploration. You always find an anomaly of interest which straddles the edge of your survey area. So let's do a third survey to define its extent. So I had limited geospatial control, and it's just me, myself, and I out on a pleasant August evening, and I ran a small grid which extended eastward. So I had you know, some rusty pin flags and some rope and a imperial tape measure to work with, and of course I had a keen eye. And with any GPR survey, there are always folks that ask questions of what the heck are you doing? You know, why is your lawnmower not making any noise? And of course, there's always some dogs that are wanting to help out with the survey. So here we have the layout of the third survey in August. Two grids, one is collected south to north and the other one is collected west to east. And here's the result of the depth slice at 0.1 to 0.2 meters below ground surface. And this is the grid from the east-west lines only. So we see there is a finite difference to these rectangular anomalies. So there is a certain dimension to these anomalies. One thing that's quite interesting, compared to the previous survey in July, we can see that these anomalies appear a little bit more dimmer. And I'm just, you know, off the top of my head, I just think that because the line lengths weren't as long as the previous surveys, the background subtraction did not have as much to work with, so they appear a little bit on the dim side. And we see that, again, these flush grave markers and the rectangular anomalies, they do line up quite nicely. Some of the profiles, this is very similar to the previous surveys. So here we have the rectangular anomalies. This is a line that's going south to north. And we can see that there are 4 distinct anomalies right here. This is a line that is going west to east. So this is going over top of the rectangular anomaly and over top of the grave marker. So the length of these is about 1.75 meters long, and the distance edge to edge between the grave marker and the onset of the rectangular anomaly is about 1 meter. Okay, probable interpretations of anomalies. Wolf stones. So I asked around some folks, you know, what exactly is this? What am I looking at? Really had no real idea what it was. So a wolf stone is very common in early colonial days in the New England states. And a wolf stone is a rectangular slab of fieldstone and is placed over burials to prevent wolves from digging up and scattering the remains. So back in those days, wolves were perceived as predators. And in fact, 20 shillings was offered for each wolf killed. And in 1742, the residents of Connecticut celebrated the elimination of the last gray wolf. And so at that time, wolf stones were no longer needed. They were largely dug up and they were used and repurposed as capstones for walls. So here is actually a picture of an exposed wolf stone from the Hartford Courant newspaper. In fact, the GPR survey was commissioned to find buried wolf stones in the same cemetery. So this one here is an actual exposed one. And the GPR survey that they did was for ones that they could not see from surface. Fallen headstones. So unfortunately, headstones, they do fall over and they are neglected and they are slowly swallowed up by the ground. So last year, I remember watching a news item on TV, and they showed some folks probing the earth with fiberglass rods to look for headstones. So here's a picture of what I was watching on TV, and this is from the Salem Chapel Underground Railroad Cemetery Project in St. Catharines, Ontario. And they're using these fiberglass rods to search for forgotten graves of former slaves who fled the United States in the 19th century. So one can actually purchase cemetery grave probes, and interestingly enough, the price point is significantly less than a GPR unit. So I see this price here is $63.89 US. So it is considerably cheaper. However, it is quite invasive. So wolf stones or fallen headstones are an unlikely cause. And the reason I say that is that the second of the two ERT profiles that was laid out in the field school in May, they went directly over these anomalies. And during placement of these electrodes, there were no indications of obstruction during the actual placement of the probes. A real quick side note, these ERT electrodes are great for grid lines for GPR grid surveys. They are easy to move and place. Okay, so back to a potential explanation of our rectangular anomalies. Infill depressions. So here we have an illustration of a burial site with disturbed stratigraphy. Of course, this is not to scale, and I apologize for that. I assume if this was for scale, we were looking at the burial site for Paul Bunyan. And at the top, we see the backhoe has skillfully leveled the depression here in black, and which was caused by the subsidence of this grave site. Okay, so why am I showing a picture of a disc golf park? So this Frisbee golf course is part of the Diefenbaker Park, and it is directly south of the Nutana Cemetery. And as I had mentioned briefly before, this is an open field cemetery. That means there are no fences or gates. So there's an abundance of foot traffic in the cemetery. People that are walking the dog, people who are interested in looking at these headstones to see when they were buried. And of course, there are the people who like to play the Frisbee golf. So they walk through the Nutana Cemetery. And of course, one of the complaints from the general public with respect to cemeteries are depressions in the ground from the natural subsidence of burial locations. So this is a tripping hazard, and I suspect that the city leveled off these depressions with a natural landscape to ensure safety for the pedestrian traffic. Geological modeling. Okay, so here we have a simple geological model of infill depressions. So right at the top, we have a couple of small sand lenses, which is adjacent to clay. RDP values of the clay are 10, and for the sand is 5. And so after modeling this and producing the resulting GPR model, this is what we get. And we see that there is a distinct difference between the clay and the sand GPR responses. We see some nice little diffraction tails at the vertical interface between the clay and the sand. And next time I have to do these, I will contact David for help, because I'm very much a newbie at creating these models. Okay, finally, some conclusions. So the typical GPR responses of burials in the Tana Cemetery, i.e. these hyperbolic-like features or disturbed stratigraphy are absent. And again, this is possibly due to the age of the burials, the coffin material, and this hard clay ground conditions. But we did find some very unusual shallow rectangular anomalies, and these align very nicely with the grave markers. And the size of these things is about 0.6 by 1.7 meters in size. The distance between the two edge to edge is about 1 meter. And of course, these anomalies are observed in the 2D profiles. The cause of the anomalies are unknown. We didn't do any soil probing or anything like that. But through some simple modeling, the material seems to be different than the natural superficial geology, and it produces a very unique signature. Understand what your applied post-processing algorithms are doing to your data. In this case, background subtraction visually enhance these near surface anomalies. And in the real sense, it is an artifact of the processing regime. And also, if one is very savvy in a pinch, GPS is not needed. We can line things up using Google Earth. So a very big thank you for the University of Saskatchewan Geophysics Department, and also the Saskatchewan Polytechnic Mine Engineering Technologies Department for the use of their GPR equipment. And of course, the Global GPR Congress and all the sponsors, and of course, all you folks that are watching my presentation. A big thank you to everyone. And questions?
Thanks so much, Randy. We really appreciate it. It was a great presentation. And thank you for walking us through, the series of investigations that you did over there. We have, I think, one or two questions in here already, but certainly everybody put your question in the comments if you have one. We've got a few minutes here for Randy to entertain some. One said grave depressions, which I guess, can they be filled by the groundskeeper with contrasting soil? Obviously, you showed that as one of the potential interpretations. Can you speak to that a little bit more, about the effects of sort of going over graves that have already sort of collapsed in and kind of smoothing them out compared to those that have not been kind of graded over again with some new soil?
Can you say that again? I didn't quite. You were cutting out a little bit.
Sure. Yeah. So the question really is about grave depressions. When they get filled in with groundskeeper, would that be a contrasting soil that would allow you to sort of see that, fill in where you may not identify that from the surface? But what if, obviously you spoke about that a little bit in your model. What kind of experience do you have with that? Do you see that, is that common that graves are getting filled in after they've depressed, to flatten them out from a landscape perspective? Or are you finding that those are, that's not kind of standard?
Yeah. So I don't have a big background with that. I'm primarily a processor / interpreter. So I just found these things very, very interesting. you know, again, in a cemetery setting, there is foot traffic. Again, this is an open field cemetery, so there is probably more than the normal amount of people that are walking. So you prevent the city from being sued or being frowned upon. They do will fill in these depressions. I did contact the city and asked about it, and they were um, I don't know if it was the superintendent was fairly new, but he really didn't have any idea if these depressions had been filled in.
Sure. And obviously with the with the tightness of the grids that you were doing, you really were getting some really nice, geometric shapes in those responses when sort of resampled back into slices. Okay, here's another question. Uh, with reflection modeling, what is the RDP? So I guess, sort of what were you using or how did you estimate, RDP? Obviously, you went through the series of processing steps that you used, but how did you do that? And sort of what's been your experiences when using, for example, like an internment to sort of do maybe a hyperbolic, a hyperbola fit, compared to some other subsurface feature that might not be as large and
Yeah.
might be a little bit closer to a point anomaly.
Yeah, so there was that water line that was in the profiles, and I used that to match up the velocity using that water line, and then as far as the values that I used in the model, I basically looked at some of the charts that you see commonly on the web or in books, and they seem appropriate. But again, I really don't know. Probably the easiest way to determine what type of soil that is would be with an agricultural probe. So this is especially in the prairie provinces, this is a big agriculture area, and they use these probes all the time. They just push a steel probe about 24 inches into the ground, and they press a button, and they bring it up, and they can actually look at the column of dirt that you have brought out of the ground. So this being a protected site, I'm not going to do any invasive um, invasive science in this. So
Yeah.
Uh,
I mean, that's another interesting point, which I am personal, would love to hear you sort of speak to for a second, is working on a sensitive site like this. What were sort of the, you know, I guess the struggles or, with it being non-destructive, the sort of ease of work, with the folks, that were stakeholders in this particular place. Kind of how did that play a role in sort of getting through this and being able to return multiple times?
yeah, so the what I understood um, talking to the professors that organized the field school, they had to approach the superintendent, and the superintendent would take that information, and it would have to be approved by the city. Um, I think that has relaxed a little bit now. Um, I think all you have to do is just go to the superintendent and ask if you can perform a particular survey. Um, I think in fact I read one form that was brought up by the anthropology department, and they are going again with the GPR antennas, and I think the next talk they're talking about these bioprobes or S4 probes, and I think they're using that technology to further enhance their methodologies for unmarked grave surveys.
Sure. All right. Final two questions in the comments. One was, what was the transect spacing that you were using? They said that they think they might have just missed it.
Transect or profile spacing 0.25 meters. Yeah.
Yeah.
So
Which I think. Oh, go ahead.
Yeah. The Canadian Archaeological Association for these unmarked grave sites that are performed a lot over the past several years now. They have a very, very good list of what parameters are used for looking for unmarked burials. And they do have a finer transect spacing because they do have young children, so the graves aren't as big as a full adult coffin.
Yeah. Yeah, and the imagery I think showed the benefit of such a tight spacing. And the final question was, how do you think a GPR survey would be affected if ground is riddled with gopher tunnels? I mean, so in this specific case, I guess, how would you try to distinguish, right, between a burial and something like an animal, burrow or tunnel?
Not sure if a 250 might capture those little gopher holes. Maybe with a higher frequency antenna, you might see some of those. I found this out from a couple of people at a recent conference. Gopher holes in a cemetery are usually indicative of an actual burial because it is an easier dig. Mm-hmm. So if you have like a whole series of gopher holes, and they line up nicely with headstones. This probably would be a good indication that you have a good grave there, and but anyway, very interesting.
Well, again, thank you so much, Randy. We appreciate you sharing your case study and your knowledge with everybody. The next presentation, which follows right up with this perfectly, like you said, is Paul Martin, who's going to be also talking about locating unmarked burials. And like Randy had, multi-sensor with ERT and GPR. Paul, has a great experience with human remains detection dogs and sort of how that pairs together. So I'll let Whitney and the other folks from Infrastructure Resources get Paul set up. Let's see. All right, there he is. So Paul, you just got to share your screen.
Yeah, Paul, you should be all set to share your screen whenever you're ready.
I can't hear you yet, Paul. But I was able to see your presentation pop up.
Okay, can you hear me now?
Yes. And Paul, can you share your screen again?
Now, can you hear me?
Yes.
Yes. And I can see your presentation. You might want to
Okay.
X out where it says always use subtitles or do presentation mode.
I don't even see that part.
I see on your screen on the right-hand side, it says always use subtitles. It says like, turn on, don't show again. You can X out. If not, you can just go as is.
Okay, hold on one moment.
And while Paul gets set up for a second, again, I just wanted to thank our sponsors again. Contour and Geolytics as being our premium sponsors, and Reveal, AccuScan, Screening Eagle, and Pipeline Engineers for contributing and supporting this event. So thanks so much. We appreciate you all helping us do this every year. Yeah, that looks great, Paul.
Good deal. So, thank y'all for having me today. My presentation is how to apply a biosensor to focus a GPR survey and enhance analysis when surveying for unknown or unmarked human burials. Just a little bit about me. I actually fell into all of this 23 years ago. Originally as a canine handler with a sheriff's department in Mississippi Delta. From there, it made me start questioning the capabilities of dogs. And I was introduced to the world of geophysics and specifically ground penetrating radar by Brian Haley, or I should say now, Dr. Brian Haley. And from there, I had the opportunity to go back to school, but along the way, I really questioned of being able to partner the dogs with um, the GPR and other geophysical tools to be able to utilize them as independent lines of survey methods for unmarked or unknown burials. And with that, the objective is to locate those unmarked and unknown grave locations so that we can prevent those unintentional disturbances on construction projects and things of that nature. So the biosensor, it's the dog's nose. And it is one of the most complicated things to try to understand. Um, and with that, I'm not going to try to give y'all um, all the ins and outs of that, but I want to give you enough information that you can walk away from today's presentation saying, okay, now I understand at least why this works. Okay. And with that, as the dog walks around, we know that they're always sniffing, they're always smelling. And what they're actually doing is they're always taking in these compounds, these odor compounds, and they're analyzing them and, sorting them out. So basically, they're doing the same process that a mass spec and gas chromatograph is doing. Okay. Except instead of plugging it into electricity and getting out this nice detailed report, uh, we feed it kibble and reward it with a ball or a tug and a pat on the head. But in a lot of ways, it's much more complicated than the mass spec and gas chromatograph, and it starts right there at the tip of the nose. We think of the nose as the entrance into this olfactory system, but dogs and some other animals have the unique ability to not only intake air through their nose, but at the same point in time that they're intaking air through their nose, they're also able to push air out through their nose. And that's where that little slit, the nasal philtrum there comes into play. And that actually allows them to help hold on to, that air and help recirculate that air back and forth inside that nostril. Another little unique thing about dogs and their noses is they can isolate whether or not an odor is stronger from the right nostril versus the left nostril. And part of that is because once they actually bring odors into the olfactory system, well, air is not just going to down the pipeline, so to speak? Well, you've got an olfactory path line and a respiratory path line. And that olfactory path line, as you can see, those red lines, it goes in and it gets filtered out several different ways. Whereas the respiratory path line, it just takes that air on down. But what all of that actually does is increase the surface area of the dog's nose for olfactory receptors. Okay. And that allows the dog to have 300 million olfactory receptors to our 6 million olfactory receptors. Okay. And then to top it off, they're tying those olfactory receptors into the olfactory bulb into the brain, which is 80% larger. That olfactory bulb is 80% larger in the canine brain than it is in ours. Okay. And so their whole world is set up a lot different than ours. So it's devoted to understanding the world by scents and smells and odors. With that, those olfactory receptors, they break those olfactory receptors down to about 800 different varieties, essentially, where we only can experience about 300 different odors. They can experience 800. That's a lot. From there, it's the different combinations of those olfactory receptors being fired off that allows the dog to say, oh, this is that, and this is that. Okay. And that's what allows the dog to discriminate between similar but unique odors. And for our usage, this is what allows the dog to discriminate between human decomposition events versus non-human decomposition events. Because we've just started scratching the surface of what this odor of death, really actually looks like. We've got 600 plus compounds. There's, that have been published. There's another study that's, pushing closer to 1,000 individual compounds related to human decomposition odor. But right now, we don't fully understand what makes human decomposition human and what makes non-human versus non-human. But we've got enough of the research done to say that the profiles between the two don't match up over time. But the way we get a dog to understand that we want them to locate the human decomposition odors is that we present that human odor over and over and over again to a game of, chase the ball, chase the toy, and reward them, for finding it and so forth, with treats and play and more chase the ball, so to speak. And then we teach them a behavior such as a sit or a down, on what to do once they have found that strongest source of odor. Okay. And then we reinforce that behavior. But there's a lot that we just don't understand on how the dog fully processes all of this, because we can't sit down and have a conversation. Well, we can have a conversation with the dog. The problem is the dog can't say, well, Joe, it works like this. And so it's classified kind of as a black box technology, because we know right now we put this input into it. We don't quite understand what happens, but we get this kind of output out of it. And so that's why it's classified as a black box technology. But one of the things that when teams have failures or lack of success, not so much a failure, but a lack of success in the field, a lot of times it's due to a lack of understanding of the odor dynamics at the spatial and temporal scale at which canines detect odor information. You're probably sitting there saying, huh? What we're actually talking about is how odor moves. Okay. We want to think about odor as being kind of this blob, but it's not. It's not constant. Think of odor in one sense as Pigpen from the old Peanuts cartoon as he's walking by, and there's just this dust cloud. Well, odor's somewhat like that, but odor also with the can also kind of be like that molten tar pit, in that it just kind of bubbles up and poof, it releases a puff or a bubble, so to speak, of gas and steam. Not really, but it releases the odor hits the environment and it's there, and then it can be carried off by the wind. But the same point in time, when we have a decomposition event, it's a little bit different when we look at burials. When we look at burials, all that soft tissue, all that ooey gooey stuff, Well, that's being absorbed into the soil itself. Okay. And it's going to create a chemical change there in the soil, and it's going to last for decades and centuries and provide a steady off gassing for centuries. All we've got to do is train the dog to understand what that off gassing is. So, some of the factors impacting odor availability with burials. Soil type. We face some of these same things when we're doing surveys with ground penetrating radar. Ground cover. We can't push a GPR through it. There's a possibility we're going to have issues getting the dogs through it or getting the dog's nose close enough to the ground. Ground moisture and humidity. Okay. Soil's too wet, we're going to have issues with the dog being able to pinpoint exactly where things are. If it's too humid, again, it's going to hold that odor in the area and again cause the dog issues on trying to pinpoint. Time of day, most handlers prefer to work first thing in the morning, sometimes right as that sun is working up, especially in days that we are going to experience high temperatures or high humidity. Sometimes we might want to work at the tail end of the day as the sun is setting, because we're also going to be impacted by the surface temperature and, as I've already mentioned, that ambient air temperature. Burial depth. The deeper that burial is, the harder it is to get odor up to the surface. Barometric pressure. The higher the barometric pressure, the harder it is to get odor to come up out of the soil sometimes. And then finally, the mortuary practices that have been employed. More modern burials where they have used these nice, gasketed coffins with the concrete vaults and so forth. That's going to help prevent odor from escaping. Also, we've got embalming that's going to impact the decomposition process. So all of those are going to impact that odor availability. But one of the other things that we need to be doing with the dogs is being able to track that canine team while they're in the field. We need to be able to quantify, hey, this area was covered, this area was surveyed. So, our case study. This is a project up at the Child's Home site and the cemetery in Maryland. The home site itself is indicated by the The white arrow, the cemetery, is indicated by the red arrow. That's the known cemetery. And when I say the known cemetery, that's the fenced in, you know, standing upright tombstones. But a quick survey around the area indicated that, wait a minute, they might not have gotten everybody included in that. Because we've got a couple of posts that are outside of that fenced area. And so those got mapped in first over by the home site just to make sure we did not have an additional cemetery over there. We started off with an canine survey. We utilized 2 different dogs. You can see 2 different survey patterns. And then over by the cemetery, the fenced cemetery is there in the blue. And then the canine survey in the kind of teal and pink. Zoom in tighter and you can see from there we've got quite a few number of responses from the dogs outside of that cemetery, known cemetery in the fenced in area, but nothing out in the periphery. Stripping away, just looking at the survey results from the dogs, we're then able to say, okay, this is definitely where we want to concentrate. But this is kind of what we're dealing with. We've been asking them for several years to clean this area up. They still didn't get it cleaned up, but using our cemetery, our fenced in area as kind of our known, taking some reference, we then surveyed as best we could outside and then grouping things together based on what we're seeing in the data. We were then able to identify some additional graves in the GPR data. Which doesn't always show up in, you know, the slice maps and so forth. From our work, we were able to identify 10 to 28 additional burials through this combined approach. Now the Bureau of Land Management can properly care for and protect these additional burials that were previously not protected or accounted for. Couple of big takeaways is that the trained canines can assist in the survey process, reducing that footprint that's needed for clearing for the GPR survey itself, but the canines should always be worked in conjunction with geophysics, and specifically, I recommend GPR. I don't necessarily feel one is superior to the other. They are definitely two independent methods that truly complement each other in a shared task and a shared goal. So, do you have any questions?
Paul, thank you so much for the presentation. I think it's a really interesting pathway forward, obviously, in the forensic space and the cemetery mapping space. Anybody with questions, put your questions into the comments. I got a lot out of it. I've personally used human raised detection dogs on a number of projects before. We don't do the dog search because that really takes, just like GPR, right? I mean, it really comes down to the user, right? And you really have to have training on that and background. And we've had quite a bit of success pairing HRD dogs, with GPR in both historic context and sort of cold case contexts. One question I have, which I'd love for you to speak on, obviously you have a lot more experience than I do with HRD dogs and GPR, is we found that the reverse is also really helpful, where using dogs to locate potential graves. Have you ever found where you get dogs that don't alert to anything and suggest that maybe there are no additional graves in an area? And how do you sort of handle that as making sure it's not like a false negative?
Yes, we have. One of the things that we do is work. So, a couple of things. We use, I'm moving away from using local HRD teams, local search and rescue dog teams, and so forth, and working with dog teams specifically for archaeological human remains detection. And with that, I am working with dogs that are used to working negative areas in these type of environments. And so I am confident in a dog team saying there's absolutely nothing there, and seeing, expecting the dog to go through an area and say, no, there's nothing in that. So, I have seen some dog teams that are coming from that's part of the reason why I moved away from working with dog teams that were from the search and rescue side of things to this, because they're not quite as in tune to this environment, and therefore they're not picking up on the older graves, and they would walk older graves and say, oh, there's nothing there. And then we bring in GPR or bring in another dog that is more experienced with this type of environment and say, no, there is something here.
Sure. Yeah, that's a great point. Not all dogs are trained for the same focus. And if you get dogs, at least in our experience, who are trained, they can identify graves that are hundreds of years old. We've had them, successfully identify burials from, from American Revolutionary War, 240, 250 years old at this point. All right, we have a question from Suzanne. It says, can you describe how the training you do with these dogs, historically trained specifically on old burials, is different from trained local SAR teams outside of running a lot of negatives?
One of the things that we're doing is, hi Suzanne. One of the things we're doing is moving the dogs away from working active decomposition, meaning the soft tissue decomposition, the fresh decomposition. We're wanting the dog teams that are working the old bone, working actively, or training actively um, within old cemeteries, within known burials, and things of that nature on a more frequent basis. Um, like my personal dog is not a dog that I would qualify to utilize on a um, forensic, you know, search for a missing person or a homicide search of a recent case. That's just not the work she does. Um, Whereas, because everything she's been focused on is 75 years or older. It's she's been concentrated for that archaeological environment.
Yeah, well, I mean, one of the really good question. One of the things that we've sort of experienced with the dog handlers that have trained the dogs, to be able to identify graves that are very old is, when you can get permissions and excavations are occurring on, um, older sites, um, getting soil samples and using old soil samples, to train again under permissions, um, of stakeholders, because it's critical to help dogs get trained to find other graves, from that point. That's one of the ways that we've seen training happen to sort of help focus, on that older scent. What about you, Paul?
Very, very much so. I'm, I'm lucky in that I walk with one foot in both worlds, as both an archaeologist and as a canine handler, and have that ability um, to be able to incorporate, you know, what I'm doing on a much regular daily basis. So I think it's so critical that the handlers that we do utilize for this um, become familiar with the archaeological community and and the GPR uh, providers out there. Become familiar with the handlers that are in the area that they could utilize for this. Uh, because the closer that these communities can work together, the better this um, partnership can work not only when it comes time to do the job, but the better training that both entities can have so that they understand what each one needs when it is time to do the job.
Yeah. What if any other questions put into the comments? But what's been sort of your experience, having a foot in both worlds, where obviously some of the examples shown in Randy's talk and in the talk that I did earlier today as well, you sort of have defined areas, right? When you utilize dogs in conjunction with GPR, how does that let you address larger areas that you sort of otherwise wouldn't be able to address? Obviously, the pictures that you show, the photos of the site from the case study, overgrown, hard to get a GPR in there systematically at all. And getting a dog to focus in on an area might help. But what kind of size areas can you address now, utilizing sort of a dog's first, GPR second approach that you think you otherwise wouldn't be able to address?
Well, one other thing, there's a project that we're working on, and I know we've done close to 50 something acres
Mhm.
with the dogs. And I know some of it has been done, followed up with GPR, but I'd hate to see what that actual, you know, try to do that with, do all 50 acres with GPR.
Mhm.
That's I know, like, we're doing 25 acres right now in 6 days, and there's no way you can do 25 acres in 6 days with GPR. Um,
What about like topography, right? How can what areas can the dogs address that are much more difficult with GPR when it comes to really variable landscapes as far as elevations and topography go?
oh, we did a project in Southwest Pennsylvania last year for the National Park Service, and it was a rugged, it was, well, it was Jamonville Glen. It's where the first shots of the French and Indian War were fired. And with it, the topography, it's a little valley area that's got steep, rugged sides with uh, a lot of rock, a lot of um, it's got a swampy, marshy area to it, the elm part of it, but it's got a lot of rock to it. The dogs can traverse that very easy, but at the same point in time, it's not really conducive to getting, you know, geophysics down in there and doing a lot of traversing or clearing, you know, the 5 or 6 acres that we were asked to survey. You can pick out from what the dogs did, you can pick out a couple of hot spots and say, okay, we want to focus here with a 10 by 10 or a 20 by 20 area at most. But um, yeah, with the dogs, they're able to traverse and really narrow that footprint down to, like with a forensic setting, narrow it down to a uh, much smaller footprint. A project we did for the St. Joseph Bay Refuge Buffer Preserve in Florida. They've got I think it's almost a 10-acre cemetery area that we were, but it's right there in that coastal buffer preserve area with the glades and everything else growing up, and you can't set up real grids to survey the whole thing. There's no rhyme or reason why trees or where they are, or anything like that. So you survey it with the dogs first, and from there, with the dogs, we're then able to go in and set up little small areas of 3 or 4 meters by 3 or 4 meters. And, you know, from there, um, what we were able to ascertain that this cemetery area, one belief was that, oh, it was started in 1840s related to a hurricane, and it was a mass grave. Well, we didn't find anything that suggested a mass grave, but the other belief was that around 1918, it was started as a local cemetery from the turpentine camps that had sprung up in the area, and men dying from the Spanish flu. And they would take people out there, 2 or 3 men at a time, and bury them there. And then possibly it was a local burying ground that for people that didn't have funds to be buried in the local cemetery.
Mhm.
And so with these kind of random placements, we're able to survey and locate, you know, multiple little areas throughout the area, and then survey back behind the dogs with the GPR and say, okay, here's this. Here is the here's what we have in this area. Here's what we have in this area, versus trying to survey or get them to clear cut
Sure.
10 acres.
The whole thing. Yeah. Well, again, Paul, thank you so much. I really appreciate it. Very, very enlightening. Again, as somebody who used dogs, I think I got plenty actually out of your out of your talk. A lot of details about how the olfactory pathways and the lobe works, more so than I've ever been exposed to before. So thank you. Really appreciate it. We're going to move on to our final presentation of the day, which is actually a panel discussion. And the panel discussion is titled Exploring GPR Applications, Bridging Academia and Industry Perspectives. And we have Forrest Sim from Enhanced Scanning as a moderator, and then as panelists, I believe that Vimy Henderson from PTech up in Canada, Greg Jeffries from down here in the States, and who is the third? Is there a third panelist? Either Hector or Jan.
That would be Jan.
Jan. Um, yes, of global fame. And Well, I appreciate you coming on, Jan, and obviously I know that you're abroad right now, and so either staying up late or getting up early and participating is really appreciated. And so I'll go ahead and hand it over to Forrest and the panelists. Thank you all so much, for agreeing to participate.
Yeah, hey, so welcome everyone to our panel discussion on academia and the private sector and bridging what gaps may be there and just having a little chit chat. So my name is Forrest Sim. I'm the owner of Enhanced Scanning. I'm a service provider, kind of specializing in some ground penetrating radar services in Southern California. We go outside of the area here, but we're mostly based in SoCal. And I also am the host of the Concrete Conversations podcast. And I would, and I'm also having a little bit of a cough and hiccups this morning. So you're welcome. I'm going to be taking sips of water every now and then. And I mean, you're just going to deal with that and be happy about it or be sad about it. But either way, you're going to deal with it, and so will I. So I'd like to introduce our guests. First, Vimy Henderson is a project engineer at P-Tech Engineering Solutions in Ontario, Canada, with over 15 years of experience. She and the team at P-Tech provide consulting to public and private agencies across Canada and internationally. Her work involves the design, performance, construction, and forensic evaluation of pavement infrastructure such as roads, highways, airfields, and industrial yards. She's an adjunct professor at McMaster University, where she co-supervises students, lectures, and has technical and leadership roles in numerous research assignments. She carries out research focused on the advancement of pavement infrastructure in Canada, considering resiliency and the changing environmental and user climate. She has published and presented her work with industry partners internationally. She is a recipient of the 2023 IEF Award for Women Identifying Business Owners. Vimy, thank you for taking the time to be with us today.
Thank you for having me.
Greg Jeffries is an industry veteran with over 3 decades of extensive experience with utilities, survey and construction, subsurface utility engineering, and utility location services. An established utility construction management expert with a specialty in addressing utility location and avoidance issues. He is well versed in all aspects of utility location, EM theory, vacuum excavation, and ground penetrating radar. He oversees SUE UC projects and pursuits throughout the southwestern United States and internationally in Saudi Arabia, Dubai, and Pakistan. Greg, thank you so much for being with us today. And we have also, whoops, sorry, I'm working with screens here. And Jan Franke. Jan, this is a little bit about Jan. Born to a deeply traditional Inuit family in northern Canada, raised by polar bears, and nourished on seal blubber and tundra grasses, Jan developed an early appreciation for the electromagnetic spectrum after a particularly nasty bout of snow blindness that left him sightless for most of his childhood. In fact, Jan's earliest sighted memory after the polar bears was that of watching a TV dinner warming in a microwave oven. After that experience, he was hooked, both on learning about microwave radiation and on TV dinners. Uniquely, Jan focused early on in the study of ground penetrating radar, earning bachelor's, master's, and doctoral degrees, all in GPR geophysics. Dr. Jan, as he prefers to be called, began building his own radar antennas for his customers' needs in the mining industry many years ago. Eventually, he also discovered a need for another software option for post-processing GPR data. So he and partner Lissandro Martinez founded Geolytics, which is also a sponsor of this year's GPR Congress. Jan has spent over 30 years traveling to nearly every country on Earth with a GPR antenna in one hand and a TV dinner in the other. Jan, thank you.
Should not have let you do that. I should have just given you a bio.
I just read what you wrote.
That's
I don't
awesome.
know why.
You
I mean,
did.
maybe I didn't use the right
Well done.
inflection. I should have said things like project instead of project and stuff like
Exactly.
that. I should have. I guess I didn't use the right Canadianisms. So
There you
Anyway,
go.
sorry for that.
Well done.
So here we are. Everybody, welcome to our panel discussion. For those of you who are sighted and also here with with your videos on, the three of you, we're going to be having a little chat, and we're going to try to make sure to include some Q&A stuff, because we're definitely going to be having some questions. I'm sure that everybody's going to be wanting to ask this really experienced group here. So we want to talk about just academia, the private sector, how these two groups get together and transitioning from one to the other and back and forth and all that. I want to jump right into some questions here. So students coming out of higher education, university, college, with lots of theoretical knowledge, but slightly more limited field experience, will, depending on their industry, have coworkers with the opposite experience profile, less theory and more boots on the ground. How much of a problem is this incongruency of training background and education? And I'll just open it up to all three of you. At the same time, go.
So if I could, I'd like to address that, because I think I've had some pretty good experience with regard to that. Back in the late 90s, early 2000s, I was exposed to Witten Technologies that was pretty instrumental in developing the arrayed 3D GPR antenna systems. And there was a lot of academia involved. Dr. Witten himself, obviously, a geophysicist, had been at Oak Ridge National Labs and was chair of the geology department out at University of Oklahoma. Incredibly bright guy. Tony Devaney, another Oak Ridge laboratory person, very knowledgeable. And then Dr. Ralph Birkin, so I don't know if he was on here today, but Dr. Birkin, also genius geophysicist, and several others that were in that era that basically great ideas, a lot of theory, knew that they could take all this theory and education and build it into something that would really provide a magical solution, so to speak, or product. The problem is they lacked that actual out in the field experience. They knew that they had a cool tool, but they didn't know just exactly how it could be applied and exactly what level of differential that tool was going to be able to make. And so we came together with them because we use GPR, really, just signal channel systems, but we use GPR daily, every day, day in, day out, for mapping utilities. And we'd actually done some cadaver recovery and things like that was discussed earlier. But we helped them kind of take all this theory and their patents and that educational information that they had and the things that they knew that were great, and then mold it into things that could be actually utilized in the real world out here, taking that theory now and in a lot of cases, I hate to say it, we dumbed down a lot of things, because they were very incredibly bright, incredibly knowledgeable, but in other words, they couldn't see the forest for the trees, if you can appreciate where I'm at. They didn't understand that they had to kind of stop thinking so futuristically and so theoretically and think about practicality and how you could take that system and apply it practically and deliver a product that the normal folks, even though they might be well educated, but they would be better able to understand and appreciate what was being delivered. So we helped them do that. We helped them kind of realize that there were some things that they did. I'll give you an example. They knew that system had to be tracked geopositionally, and so they figured out that back then GPS reaction time to the GPS was much too slow. for a moving GPR system. And so they went to authoritation, which was smart on their part, but they never thought about project control and really, if you go true spec, go out and they would set up a total station, if you will, on top of a manhole, and that would be their reference point for the entire job. And they would scan the system and they would take that data and then they would tweak it back into that manhole lid. And the problem was basically they had a lot of great information, but once they did that maneuvering and tweaked it back into fit to the manhole lid that they identified, all geospatial accuracies and positioning went out the window. And they just couldn't appreciate why that was. And so we helped them refine some processes, identify how we needed to establish, survey control and so on, and give them very specific reference data that we, surveyed to beginning prior to the job, pre and post on the project, and help them then turn that information into a CAD deliverable that was then really relatable to the engineering world rather than just the imagery that they were basically presenting. Anyway, I think that's where that bridge, like you talked about, between academia and all that knowledge and theory and everything that they have, really needed the field folks, if you will, the guys that were versed in application to come together and mold those two pieces together in order to make it a really viable deliverable.
Thanks, Greg. Vimy, you have any thoughts on this, on how much of a problem is it having and maybe maybe I'm being presumptuous here and just projecting my experience onto everyone else's here, but do you see this as a problem of there being a disparity between what university students are graduating with in terms of experience and knowledge and also expectations for what to find in the private sector, and then what they're actually discovering once they get a job and they show up day one and start using GPR out in the field?
Sure. I think it's a challenge for any industry, whether it's GPR or our various sectors of engineering and whatnot. It doesn't matter how long you went to school for, you're going to learn how to do your job when you get there. So I think the important part is you go in open-minded and aware of the fact that, all these individuals around you, whether they've been doing it for 5 years, 10 years, or 35 years, they have a lot of experience and you have more to learn. And, if you, depending on, what you did, if it's what we would call, a technical diploma or a university level degree or grad school, you come with different skills, and, you start to see the benefit of those skills as you progress through your career, I would say. But right out of the gate, you're going to get the most out of it if you're open-minded to learning from the folks with a lot of experience. Jan?
Yeah, sorry. So you're absolutely right. This is not unique to the ground penetrating radar industry by any means. This dichotomy between having theoretical knowledge and on the ground, boots on the ground experience. But there is something unique about our specific line of work that I think we need to address because, and I speak about this all over the world. I teach university students in universities and on every continent. I'm here in Sri Lanka right now, actually. And what we see is that if you go back in time to the 1990s, ground penetrating radar was the specific domain of geophysicists. It was a geophysical tool, just like seismic, ERT or MAG or anything else, right? And you needed to have some basis in physics And even utility detection was done by a geophysicist. And what happened in the late 1990s is that the manufacturers, the three of them basically at the time, Sensors and GSSI and Mala, ran out of geophysicists to sell the damn things to in the first place. So what were they going to do to keep their businesses afloat? Was come up with words like easy locator. And what that did is it democratizes the application of geophysics for certain applications, right? So they tried to dumb down the instrumentation and attract the non-geophysical crowd to do more simple tasks, which I'm not saying that, finding pipes in the ground is simple, but it's a little bit more straightforward than other applications. And that was great for the business in itself. But what it created was this bifurcation of two different types of the use of GPR, where some of them, and 80% of the clientele, were guys that were buying it. They could have been plumbers, they could have had some engineering background, but they were just using it to find hyperbolas on their data sets, relatively straightforward. And then the hardcore geophysicists who were doing the more complicated stuff around maybe archaeology or geology or whatever. And today, there's back to Forrest's question about this theoretical, there's a need for both of them, but I question that we shouldn't put everything in the same basket, right? So for example, I think Ryan North is on this call. In Canada, for example, in many provinces, let's say specifically British Columbia, Saskatchewan, Alberta, Ontario, and probably Quebec, you cannot practice geophysics without a license. It is illegal. And to have a license, you better have a geophysics degree or something relevant, right? Now, here's the question. What is geophysics? Is the guy who's got sensors and software, 250 megahertz, going across Main Street, picking up a pipe, is that geophysics? Well, it used to be, in which case, is he breaking the law, right? Like literally, is he breaking the law? So there's many other questions to ask around experience and technical knowledge. I think there's a need for both of them, but I think we can't lump it all into one, right? Like certainly I would feel that if you're doing utility detection, that's more the realm of perhaps a community college level level of academia and a heck of a lot of on the ground experience compared to perhaps somebody doing some much more complex work around archaeology or geology, where I do think that on the ground experience is not that important. I mean, anybody can push a cart or drag a snake around. It's what the heck you do with it and what it all means.
So is there much emphasis in college courses on commercial applications, on an emphasis on commercial viability of these of the skills of learning how to use ground penetrating radar, or is there a lot of kind of, I don't know if this is a good term, but science for science sake? I mean, there's and science for science's sake is a noble and good and ultimately commercially viable endeavor. Look, I'm no historian, but even I know that the space race to get something in orbit and to get something to the moon and to get something to out past Jupiter and Saturn, that was science for science's sake, and it just so happened to create most of the technology that we enjoy today. And so I'm not trying to dismiss the value of just pure science, but where is the emphasis in college curricula? Is it on the science, or is it on, okay, guys, once you leave college, you're going to have to do this thing called getting a job. And if you don't have some skills that are actually commercially viable, we're not doing you any good here. Where's that balance?
So
Okay, hard. No, go ahead.
Okay, so I do have a little bit of experience from an outsider perspective coming into post-secondary institutions and doing courses or workshops around near surface geophysics and GPR. And the answer is, again, times have changed, right? Like the great advancements in GPR from a research perspective were done. They were done in the 1990s. They were done in the 1970s and 80s. There's not a heck of a lot more we're doing with GPR, to be honest, right? I mean, manufacturers will lie to you all the time and use fancy terms like AI and all sorts of things, but it's GPR is GPR. It's done, right? There's not a heck of a lot more we're going to do with it around the technology. So what happens is all the higher level, the tier one schools are unfortunately moving away from GPR and looking at other things. And then you have the more community college and the second tier or third tier in the United States, as you call it, the state schools, I guess, that are still doing more practical hands-on things. But what's interesting is when we look at the numbers in near surface geophysics, man, they have dropped in the last 20 years dramatically. Like nobody wants to do it. It's just not a thing. And I was just in Australia a couple of weeks ago, and we're trying to, how do we make this sexy? How do we get people into geophysics? Because there's other cooler stuff that pays more money these days, right? It's hard. And even the oil and gas industry is not doing there's not a lot of graduates in geophysics compared to the 80s and 90s. So it is a challenge. And to answer Forrest's question, I think there certainly are some schools that are still doing very interesting stuff, but all the big stuff that was done has been done. So it's hard to keep rehashing the old thing, right?
True. Yeah. Most of indeed, by sometime in the 90s, GPR had basically, that was it. Most of the development had been done. I mean, they used GPR. So it's basically settled science, if you will. I think the only thing that's happened really since then is some signal processing improvements, that they've been able to refine that and been able to kind of refine some of the delivery methodologies where they make the instruments a little more user friendly, a little more sexy, so to speak, and kind of window dressing, really. At this point, they keep adding new facade to basically the same technology. So yeah, I totally agree with Jan that basically it's settled science now, and what's the next thing?
Yeah, and so
I don't teach geophysics. I teach pavement engineering, but certainly on our side, it's one of the types of data collection we talk about. Not teaching you how to do it, but demonstrating the benefit of it and the data we're getting from it. And certainly coming back to your first question a little bit, GPR is a little bit different for us, or at least, okay, I've met both sets of people, folks that think they can do everything and they can analyze the GPR and they can drill boreholes and they can design the pavement and they can do it all. But my preference, and certainly I think the folks I align with more, we're going to hire a geophysicist to analyze the data. And I've had wonderful experiences, working on international projects and so on, where they've had, interesting failures. And we collected the data and worked with experienced geophysicists who were able to point out different things, and then we could combine our understanding of the pavement structure and say, maybe that's this. And they said, oh yeah, that could definitely be that. And, if I looked at it there, I wouldn't get past the beginning if I was trying to do it myself. So it's a little, we use geophysicists as specialists to complement our work, certainly.
That's great. Thank you so much. And everyone, we've got a fantastic panel here. Make sure that you're putting some comments or some comments for sure, but also questions in the chat here, so that once we get some built up there, we'd like to come in to the chat and just start answering your questions directly. Highly experienced panel here, so give them all your hard questions. Next hard question: what does academia need to learn from the guys who have their boots on the ground that maybe academia is not picking up on, and vice versa? What do the boots on the ground guys need to understand that academia really brings to the table here? Because you'll have both camps of, I understand we've got a very, what's a nice way to put this? Very level-headed, reasonable group of panelists here, where you're all understanding, except for Jan. I mean, it's the polar bear stuff that got him a little screwy in the middle. So anyway, but there are definitely those who are on the extreme ends of that. The guys out on the field. I remember I've given presentations to guys like this before, and they see no use at all whatsoever for anybody who's spent any time within the walls of a university. And on the other end of the spectrum, university professionals, professors, or just those who have a lot of higher education, who don't see that anybody without a university degree should even touch a ground penetrating radar antenna or do any level of interpretation at all, regardless of whether you're doing concrete investigations and voids or just mapping rebar, simple things like that. So the extremes here, I think most people aren't in those extremes, but there are those that have a harder time seeing the value of the university experience and the university seeing the value in the field experience. What do those two need to learn from each other that they might not be? How are they talking past each other?
Yeah, they need to learn that they do need each other. There are those in my experience, that are kind of strictly on the academia track, right? They've um, received advanced degrees in geophysics, electrical engineering, radar theory, all these things, and can't think beyond the four walls of the institution as to just exactly where the practicality of those things might rest. And then obviously there's the guys in the field, like you mentioned, that I've heard it. I don't have any use for the egghead, um, to come out here and tell me how to, use this GPR. I know exactly what I'm doing with it, and I know what I'm looking for. Um, but they need each other. They need to talk to one another. I learned honestly a great deal from guys like, Ralph Birkin and Alan Witten and those guys, because they were incredibly smart and taught me a lot of things about geophysics that I would not have otherwise learned. And then taking my practical field knowledge and thinking about what I learned from them, and how can I apply that out here in the field, and how can I teach other people how to appreciate what they've taught me and apply it out here in the field.
Jan and Vimy, any other thoughts on how academia and the private sector may be talking past each other and not really connecting on the value that the other can bring, or personal experiences that you may have in that realm?
Yeah, I mean, this is somewhat rehashing the original point, right? That there's this dichotomy between the technical knowledge and the boots on the ground experience. And, from a very practical standpoint, yeah, I've been doing this for 34 years. I build my own radars and I write my own, well, I don't write my own software. Lisandro writes software, but I tell him what to do. And if I was doing a utilities section survey, I would want Forest on my site because I have no idea what the heck I'm doing. I understand what the data is going to do, but I don't have 34 years of experience of getting around a light post, or how do I set up this GPS that's not working. There's value for both, absolutely. And what we're also seeing, because I get to see this through geolytics, right? What we're seeing more and more, particularly in Europe, which is, let's face it, ahead of North America, is that these companies getting bigger and bigger, and they have the field guys in the field and the knob heads in the office. And I think that's a really good place for both of them, right? Because we don't need the field guys necessarily trying to understand the polarity of a specific signal to understand if it's a void. Who cares? Just get the best data in the right place that we can, and then let the knob heads back in the office do the office stuff. And we're seeing that on larger and larger businesses now, that this is commonplace, right? In the past, it was a one-man show or two-man show, and now so much of this are larger companies that really bifurcate the responsibilities.
True.
Yeah, thanks very much. Vimy, anything to add to that?
I think the important thing, and yeah, you're not going to change the folks that are at the far extreme of each end, But let's work with who wants to work together, and the opportunity to collaborate um, between industry and the students or academia, and whether it's sessions like today and encouraging participation. And as Greg said, um, or maybe I'll paraphrase, you don't know what you don't know, but sometimes you sit in a session like today and you hear something, whether you're on the academia or the industry side, and you're like, oh, I should take that back to the work I do. And always sometimes it's easier when you work for a smaller company, than in the corporate structure, but the opportunity to give guest lectures and work with academia a bit, and if you have a project, whether it's a fourth year idea for a fourth year design project or whatnot, but build those connections. And as academia, certainly the work we always do is very industry driven. The intention is that it's going out to industry, which, as you said, is not the purpose of all research, but eventually, likely, there's a benefit to the industry in the long run.
Thank you. We've got a question in the chat here. I'll start going through some of these. It reads, how often are academic institutions engaging with professional communities to ask, what do you want new hires coming into a job knowing and capable of? Is there a forum for academic communities to talk with the other side, to talk with the professional communities and figure out if they're producing the kinds of professionals that the private sector needs? Does that forum exist?
So I can maybe add one comment there, and I don't know if it does exist in the geophysicist, degree and so on, and training, but we have co-op or intern programs at some of our Canadian universities, and I went through a co-op program in undergrad, and that kind of drives it back to the academia, because the students go out and work and they learn things and they see things in industry. And then when we go back to lecture the next term, we have different questions for the professors than if we hadn't been out working. So that shapes those programs. I don't know if you have similar situations in other degrees.
One of the challenges that I come across in post-secondary institutions when I lecture there is that, if you have an undergrad course, it tends to get rehashed by the same prof year after year, right? So, you'll go to the UK, for example, and they'll have a really good course around concrete rebar mapping. They'll have a GSI antenna, and they do the same thing on the same piece of concrete year in, year out. And I come along and say, hey, that's great. That's one application of this great technology. But did you know that you could use GPR to find cancerous tumors in human breast tissue? And the students are like, what? Oh, I had no idea. Or did you know you can map glaciers in Greenland 3 kilometers thick using the same technology, right? So and I'm not saying I'm not denigrating professors in any way, but they kind of, and again, Vimi's certainly an exception, but they tend to rehash the same things over and over and may not themselves be aware of the great, the tremendous variety of applications that our specific field has. And it's unique in that sense, right? No other type of tool, be it geophysics or really anything else, goes from everything from a tumor all the way to kilometers of glacier using the same technology. That's cool. And it's not just about finding pipes in the ground or rebar in walls.
That's fantastic. Thank you. Another question here, does the professional need come from legality and liability? How much of a role does the litigious nature of our society play in the need for formal education and training?
Well, okay, I'll jump in again. Sorry. So the history of the professional geophysicist and the professional geologist comes from the 1930s, and there was a lot of snake oil salesmen in the oil and gas sectors, both in Canada and the United States. And there needed some legislation around that could verify somebody's credentials and provenance. And when they have a stamp, it actually means something, and that goes all the way to investor relations. So that's kind of the background of it. And then the mining industry came along and said, hey, we need this as well, because if a geophysicist is producing data, which then a geologist claims has $2.5 billion worth of gold in the ground, for example, well, that's going to the stock market, and we need to have some sort of verification that this guy knows what he's talking about, right? So that's fine. But how does that translate to what we do at GPR? I mean, we're not creating, stock portfolios out of mining companies generally with GPR. I do, but mostly we don't. Well, that bridges the gap into more of architecture and engineering, where it's not about investor relations, it's not about oil and gas deposits, it's about risk and potential for an accident, right? An engineer building a bridge needs to have a professional engineering designation, or else you don't want to drive across that bridge. Well, that's where our world is. And if you look at it, what's more important? Can a geologist actually cause somebody to die? Probably not, right? They're not going to cause a fatality, but all of us could. If we completely miss a gas line and somebody sticks a backhoe into it and it ignites, that's a potential fatality. So one would think that this would be much more legislated than it really is. I mean, I find it ludicrous that there's not more legislation around even utility detection, regardless of how simple it is and how simplified it's being made by the manufacturers. There is the distinct possibility of a fatality if you get it wrong. And there's very few other professions, other than medicine, of course, or engineering, that you could actually kill somebody.
This is a great point. I think, the need for public safety, driving the need for licensure, and the licensure requirement driving the need for the education, so on. It kind of works backwards.
Well, and Jan, so your experience has been predominantly, or at least heavily, in mining, and you
Yeah.
can speak to that quite a bit. Greg, your experience is very very strong, very heavily in the utilities side of this.
Correct.
What has
Correct.
your personal experience been with, anecdotal or not, but what's your personal experience been with the legalities that, or the litigious problems that we run into with a licensure not existing for the for utilities detection in, I think, all of North America at the very least?
Well, I deal a lot with that almost daily with regard to utility damage investigation work. There's a number of people out there that think that they know exactly what that instrumentation is saying or doing, or they know how to interpret what that instrument is telling them, and um, they really don't, or they have a false sense of what that instrument is telling them, and we end up with these damage incidents. And like Jan said, I mean, hitting a gas line, hitting a power line, those things can be deadly. I refer to them as the things that go boom. Um, if you miss a water line, okay, nobody's probably not going to die unless they fall in the hole and drown. Uh, but a gas line has the propensity to kill multiple people. Certainly hitting a power line has the propensity to at least kill the operator and the people that are in the immediate vicinity of where that strike happens. Um, and I think not having some form of, I'll say, certification, for lack of a better way to put it, gives people the false sense that some guy showed up, and because he pushed around the GPR, or he swung a electromagnetic detection device, that somehow he was able to tell them precisely where everything in the ground is, and they can go ahead and put a shovel in the ground and be safe. And that's somewhat scary.
Right. Bimmy, your experience is more structural and pavements and things. So again, a different perspective here. Could you speak a little bit to your perspective on the topic of legal issues that can come up with the use of ground penetrating radar?
Yeah, and building on what Greg said, I mean, yeah, probably no one's going to die if we hit the water main with the borehole, but it's not going to be a good day for us. And there's going to be costs, and no one's going to be happy. And yeah, you don't want to scare anyone off. I mean, we already talked about challenges of getting people into the industry to begin with, but there is a risk. It should be understood that there's a risk with the information that's being produced and delivered, and if we're relying on it, there should be some responsibility from that data that's being provided, or you can't place reliability on it, and it's to be used in your own, as you see fit as a professional, and then that's the case. But yeah, I mean, there's certainly risk in everything we do, and we have to find the balance where the risk sits. But there's nothing bad with putting a little pressure on that, something could go wrong with the information you're providing. So pay attention and do it, make sure you're qualified to do it.
Yeah, for sure. We're kind of in the chats here. Some of the comments are starting to get back to some of these ideas of training, and I wanted to touch on this question. This might be our last. We might have one other question after this. So, and I'd like each of you to answer this one, please. If you could wave a magical wand to create the ideal training program for prospective GPR professionals, describe what that would look like. What would the classroom to field experience ratio be? Would there be on-the-job training options, or should all GPR professionals take and pass university level courses, regardless of their applications? Or should some GPR applications, antenna configurations, project types require formal university instruction and training, while others don't?
Well, I think that there should probably be a healthy mix between, if you will, academia and field folks, practical knowledge folks. I do think that it makes a lot of sense to consult with your geophysicist, even if you're doing utility location with GPR. Consult with your geophysicist or your person who has that level of knowledge or experience with regard to GPR signal processing and understanding just what that data is telling you. The thing that I see nowadays is that the manufacturers have made these things really pretty simple to operate. It's just like flip on a switch and off you go. And for the most part, they're well accurate. They're very accurate pieces of equipment, but there still are some interpretive values. What is, because there are a lot of things in the ground that will ring out a hyperbola. Is that a utility? Or is that the target thing that you're looking for? There's some, I'll call them false positives that get interpreted. But I think that putting together a class, I would say that it needs to be a fair amount of folks that are knowledgeable in the theory and can explain the theory and then can explain some troubleshooting techniques, but at the same time explain when they should then look to a resource that understands the data um, in the theory behind that data, better than the general person pushing the GPR would understand that data.
Jan, care to chime in on uh, the on an ideal training program if you could wave a magical wand and make it happen?
Okay, so my experience is that there are um, two issues with GPR practitioners that I ran into worldwide. One is the old adage that if all I have is a hammer, every problem becomes a nail, right? And that's again, either being very optimistic in their business outlook, or that's all they have and they want the project. But so often we come across a lack of basic geophysical skill sets that says, hey, GPR is not the right tool for this. In fact, quite often it's not, and there may not be a tool at all. So that's one of the problems. And certainly, regardless of levels of education. For example, I was just in Qatar about 3 or 4 weeks ago, and I was teaching a company there, and two of them were PhD level geophysicists, right? So what the hell am I going to teach them? Well, it turns out they've been doing utility detection for years there, quite often with lines spaced 50 meters apart. And they say, hey, that's the way we were taught. I'm like, who the fuck taught you? Like, who is this, right? Where'd you get this knowledge? Because what the heck's the risk you're putting into your project? So I don't know if it's as simple as an education, but what does that mean too? I could get one on the back of a cereal box if I wanted to and call myself a geophysicist, right? So there's a little bit of a danger in that. But I think what you sometimes see in other professions is, hey, you get what you pay for. So for example, you could have a service that says, hey, I'm not a professional geophysicist, so I'm not going to sign off on this, or I'm not an engineer, but I'm going to charge you $800 to do this. Or you can go to the company down the street who is going to verify it, and it's going to do a little bit of perhaps a better job, more precise, and it's signed by a professional geophysicist, but he's going to charge you $1,200, whatever the case may be. Maybe that's, the client needs to be made aware that there are risks involved with different levels of experience. And I don't know how to quantify that.
Yeah, that's hard. Vimy, do you have any thoughts on this one? If you could wave your own Vimy magical wand in a magical place where everything goes her way and there are no problems, what would Vimy's training program look like?
Well, I'm still working on sourcing that wand, but my one comment to add to the others is, and certainly as we're, trying to keep people or get people interested, is being able to share enough examples, whether it's through a co-op program, but at least in lecture or in, um, in the training that's from individuals in industry or examples from industry. This is the type of work you would be doing or you could be doing, right? From the utility side to, we were talking about working with dogs and so on, in partnership in the session before this. So, there's a wide range there of work they could be doing. And I think that is something that's always very difficult for students, I think, and even professionals in a lot of fields, when they're 3 years into working, understanding, am I ever going to get away from filing locates? Well, yeah, but you have to do this first. But this is where you could go in this direction or that direction. So I think that's an important part to any education program.
Thank you. Let's wrap this all up with one last topic. It's been brought up by a few different people in the chat, and Ryan North put it pretty succinctly here. He said, "What is a GPR professional?" And I know that Ryan and I have actually had conversations about this. GPR. He's not on the he's in the chat, but he's not on the panel here. So I hope I represent a part of his views accurately. I'll do my best. But we've chatted about this, and that he's explained that you don't call a framer like a hammer service provider. That GPR is a tool, and it's one of many tools that can be used for many different things, and and it takes training to be able to understand, as Jan, as you were saying, it takes training to understand which tool is the right one and which circumstance, and then you get into all the other parameters within that tool of the of designing the survey, designing the investigation, your transect spacing, and your I mean, just so many things. The frequency that you need to be using. There are so many variables there that have to be decided upon in order to get the best data possible out of this. And what all goes into being called a GPR professional? Is that even a name that makes sense, or is the case that GPR is such a unique tool that it is that we can use a title like that, or should we just kind of trash that?
I kind of like the way right now ASCE is looking at some certification programs, not specifically GPR, but with regard to utility detection, utility classification, utility investigation, and so on. And those programs are taking essentially the field folks, I have a hard time saying the non-professionals, but you want to look at it like, okay, these are the technologists. So I tend to look at it like this. So the guys that are pushing the GPR out in the field, those are the technologists, those are the data collectors and whatever. And then I look at the licensed person as being the GPR professional, if you will. So, and I think it makes a lot of sense in that regard that you have the technologist who certainly, appreciates the operation of the device, understands a fair amount of theory, understands how to lay out a job, arrive on a job, lay out a job, understand the number of transactions that have to be made, what spacing do we need to work with, and so on. And then, refers back to that professional, the GPR professional for some higher level interpretation or guidance on improving what he's doing out in the field. That's kind of where I see it, and I think I agree with where ASCE is going with this idea of certifications for those folks that are the technologist folks that are essentially, they may have a lower level degree, like associate's type level degree or whatever, or maybe not. But they certainly have amassed the knowledge to apply the technology. And then, of course, you have those folks that have the more advanced degrees that perhaps understand the theory and application from the professional side much better. And obviously, they are able to get a professional license. And I agree with that kind of step between the two. I think it makes sense.
Thanks, Craig. Vimy, any closing thoughts on the term GPR professional and what that even means, if that has a meaning, or should we just be doing and saying something else that's more accurate to reflect what's going on in the field and to reflect their level of experience and training?
I'm probably a bit removed from the correct or the industry standard terms and whatnot. But certainly that is a term I would use, and I would use it as Greg explained that, when I am working with a geophysicist, I would, think of and have no problem calling them a GPR professional. And my intention is I'm able to call them and tell them this is my problem. And as Jan said, do you think we can use a GPR to collect the right data for this and maybe find the answer? So that's certainly my idea of a GPR professional. They have the experience, and they can they can give me some guidance from that side and interpretation of what the data is telling us or not telling us.
Yeah. Well, and a lot of your various and differing views here are very representative of at least my experience in the industry, in that I have friends who are pretty hardcore on one end or the other of all the topics we've discussed. I have friends on each end of this, and I think these discussions that we have in a public setting like this with some input from the audience, I think is very, very important. And I want to thank all of you, Greg, Vimy, and Polar Bear Jan, for your time here today on the panel. It's been very fun. I found it interesting. Look forward to going back through the recordings later and just being able to watch this over again and be able to refresh myself on the things that you've all contributed to. So thank you very much for your time today. I'm going to turn this back over to Mr. Big Man for closing us out here today on the GPR Congress.
I mean, Sam Whiffen is now posting polar bear images into the.
Thanks.
Well, now that I'm sitting on the panel and somebody gave me the bright idea of putting your view into together mode, they said you won't regret it. I did not regret putting my view into together mode while watching this panel. And you got to have Lissandro code something like this, into so people can see themselves in a really interesting background. But I just want to say thank you so much to the panel members and to Forrest for moderating this panel. We appreciate everybody's perspective. This is the 4th year that we've done GPR Congress. We just, we hope that everybody gets something out of it, right? When we started this, Forrest Infrastructure Resources and myself, there was nothing like this out there. I don't think that there still is anything like this where folks from all over the world can get together in a single day, hear new presentations, hear a topic for discussion that's sort of relevant in the field at the time. We see a lot of people returning back to this each year. And participating, in the comments. Look, Ryan North, for example, right at the end with the closing question, has always been offering insightful commentary and questions for the panel. And I feel like it's developed as a really nice community. And I want to thank also all of the presenters, throughout the day, Paul, Randy, Stephen in the beginning, and Davide. And again, I want to just say it as every year, Infrastructure Resources helps this thing go off without a hitch. There's virtually no technical problems. They run all of the back end for it. They make sure everybody has the right link. They make sure everybody can get in, can ask questions, and just, have committed to putting on such a great show every year. And so there is going to be, I guess Levi's going to put a survey into the chat. Please take the survey. It's really helpful for us to understand if we should do this again. It's helpful for us to understand, if we do it again, what should be in there. Should we bring back a presenter? What topics for discussion do people want to hear? And of course, I want to thank the sponsors who make this happen every single year. Contour, who's been with, and Geolytics, who've been with us for a long time in supporting this event. The Global GPR 24 Geolytics coupon code is in there for a free, I guess, month. I encourage everybody to check it out. Our team uses it daily. That software is just really fantastic, and the support is excellent. I also want to thank Reveal, AccuScan, HSC Pipeline Engineering, and Screening Eagle for supporting the event as well. And these are folks who just want to put back into the community and make sure that there's a forum like this. So we appreciate everybody. Thank you for showing up again. And I hope to see everybody next year. Somebody said, "Hey, wish there was more than one of these a year." It's hard to put it on once a year, but we'll see. But if we get enough positive feedback, we may consider other opportunities as well. So thank you so much. I appreciate everybody from around the world tuning in, and reach out if you have any questions. And the video replay of this will be available shortly at the GPR Congress website. So thank you. Appreciate everybody. Another great year for GPR Congress, and I'll see everybody soon. Take care.
Thank you.